Hi, all. Thank you for coming to the last day of the Improving Scientific Software Conference. Today, with no keynotes, we're just going to jump straight into talks. And we'll have a break, another set of talks, lunch, and then that'll be the end. So to kick us off, here is Felix, who will be talking about a transpiler for migrating legacy x86 to ARM. So yeah, Felix, take it away whenever you're ready.
Yeah. Hello, everyone. Welcome to this talk. I'm Felix Nshuti, a student at Carnegie Mellon University, Africa, studying masters in electrical and computer engineering. Today, we are going to talk about how we can inspect the translation process of migrating from the legacy x86 assembly code to new emerging architecture ARM assembly code using an inspectable compiler-based pipeline that is implemented on top of LLVM infrastructure. So the main motivation of this is that there is a portability, or it has been observed over the time, there is a shift in the architecture from the CISC systems to RISC systems, and we have seen that technologies like Fugaku, AWS Graviton, and Apple Silicon are now migrating to ARM-based architecture. And the main challenging problem is there is a lot of hand-optimized x86 assembly code that is incompatible with ARM assembly. And doing the manual rewriting is very error-prone. It requires a lot of experts, and it is costly. So there is existing approaches to solve this problem. We have seen technologies like Rosetta and Kemu. They only work on the binaries, so they do dynamic binary translation. We can have manual control where we have experts rewriting the existing codes into the new emerging architecture. And then there is LLM-based transpilation, which is more probabilistic, and it requires more compute to run the inference of the predicting the translation of the code. And what I've seen that is missing is a static, transparent, and inspectable tool where you can, at every stage of translation, you can inspect if you are getting the correct results of depending on your intended application. And it can be modular to extend the support of existing instructions and add more optimization passes to improve the runtime and efficiency of the generated assembly code. So the design philosophy of this project is that we have the static transpilation that works on the source code instead of binary code. And then there is full transparency at every stage, as we will see in the coming slides. You can inspect the intermediate stage of your translation process. And then it follows the compiler architecture, which makes it modular to be extended to support various instruction set and different input types. And it relies on top of LLVM, which is a powerful compiler infrastructure, means that it will be easy to deep dive into the implementation of the project, and you can easily get the support online because many people are using LLVM tools. Yeah, you can see that we can be able to inspect the token stream, the abstract syntax tree of the captured semantics from the input code, the intermediate representation before and after the optimization passes, and then you can still inspect the output ARM assembly code. And for now, the code base is almost 5,000 lines of C++ 17 standard. Yeah, the pipeline is designed as a standard compiler pipeline, you can see we have the front end, the middle end, and the back end. And the front end is made of the Lexa, that is a trie-based that classifies the input instructions like variables, immediate variables, the macros, the directives, and memory addressings. Then it passes that tokens to the parser that builds the as abstract syntax tree that is then used by the LLVM intermediate representation generator API to generate the intermediate representation of the input code. Then we can implement the optimization passes. For now, we support the native LLVM optimization passes. Then in the backend, you just have the LLVM backend that generates the assembly code to the target architecture. So the inspectability of the tool is that at every stage, you can inspect the intermediate values with either using the verbose or emit intermediate representation at the IR stage. Yeah, as we said that the supported instructions for now are the data movement, arithmetic instruction, multiplication and division, bitwise instructions, compare instruction, control flow, and some of the system calls from x86. Yeah, this is the main structure of the abstract syntax tree that is extracted from the input. And you can see that the sections the text, data, and BSS sections are generally passed independently to ensure that we are capturing the correct semantics of the input code. Yeah, the current implementation of the intermediate representation is register model, where we try to simulate every register by using alloca in the entry block. And it's still like a bottleneck for the implementation, which is something that I'm looking into currently. And it's the workflow is that the entry block allocas are promotable by memory to register operation in LLVM, but this is done at the optimization phase. If you are doing without any optimization phase, you are having a simulation that is a stack that has registers in it. Every register is allocated to its own stack variable. So seeing the tool in action, we can have a simple greatest common divisor Euclidean algorithm that is a subtraction variant. We tried to simulate to try to transpile the input source code that is computing the GCD of 48 and 18, and we know that the result is 16. This is the source code from the x86 assembly, and the main covered part of the transpilation instructions that are covered are these: the data-dependent branching, the jump instruction, subtract instruction. Yeah, we can see that in the LLVM intermediate representation, which is the key component of our project. As when you're implementing the optimization passes, you will need to optimize the intermediate representation before you reach the compiler backend. You can see that every register is simulated by using alloca without any optimization pass. This is when we have the O0 optimization option. And we can see that alloca is taking 10 instruction. We are having 10 alloca instruction. Then each entry block has 5 instruction. Then we have 2 loads instruction per loop iteration, and we have one store operation per every register write. And this is somehow a bottleneck of our implementation. And when when you use the optimization pass 1 or 2, the mem2leg will improve this by using the static single assignment values and eliminate almost every these of alloca instruction that we have previously. You can see that when we use auto optimization, our root has collapsed into just one block, and we just have another fee select that is encoding the root state and the branch logic, eliminating those allocas that will slowing our implementation and introducing the overheads of many instructions. You can see that the file nodes, they carry Hrpcek carried values. It means that they simulate our alloca instructions to be more efficient, and then they replace the control flow. Then we have the fewer branches, which means that we will have the improved instruction scheduling and the backend code quality will be good. That's why we have seen that the optimization 2 drops the heavy stack traffic to register resident code, because we have seen that every alloca is now is a stack variable that is having almost 10 assignments that are redundant. Yeah, we can see that at zero optimization, we have the stack speed overhead. It means that we are having many of LDP, LDR, and STR instructions that are keeping the virtual registers in memory, because we are almost simulating every register behavior from the source of x86 instruction and translating to this code. So we've seen that the O0 loop has 20 instructions per loop per iteration, and when we use the optimization 2, we have the loop states are kept in register to avoid that stack simulation, and we have more efficient and reduced instruction output code. So you can see that with no optimization, because we are simulating the register as stack components, we have the stack frame of 12,000 bytes. And when we use the optimization 2, we just got few instructions and the stack variable was eliminated because the stack state are kept at a register level. So we just have generally at the intermediate representation, we have 3 optimization passes where the O0 is no optimization. We've seen that we have 1 stack slot that is simulating every register. Then we have the O1, which is LLVM O1 pipeline. It uses mem2leg to promote the allocas to static single assignment, and it just eliminate more of the load store overhead. Then we have O2, which is the full LLVM optimization pipeline. It does the dead code elimination, constant folding, loop optimization, and instruction combining. Then when we are doing the code generation, this is where we implemented our optimization passes, but they are mainly optimizing the generated intermediate representation. Yeah, I tried to benchmark some of the programs by comparing the instruction count and the expected return status of every function. You can see that in x86 we have some instruction count, and when we don't have the optimization, we can see that we have a high jump in instruction count, and And when we optimize, the instruction count will be reduced, and it is expected that obviously the instruction count for ARM-based ISA will be much more compared to the x86, but at the optimization level, it will be in some tolerable numbers. Yeah. Yeah, this is that we've seen that there is a drastic shift in the optimization passes, and the good thing is that with this framework, you can implement your own optimization passes and integrate them at the stage of the intermediate representation generation. So we've seen that the O1 and O2, they almost capture the same optimization patterns in the tested code. This is the graphs of the optimization of the comparison of the output, which is more of description of the table above. So we've seen that there is for all 13 programs that we tested, there is identical instruction count for O1 and O2 and the text size, because we've seen that the O1 will eliminate allocas, then O2 will implement the loop optimization, the dead code elimination. So actually, we've seen that the main optimization that is being done here is the alloca promotion. So once we remove that, we will have this instruction, because they were the ones that were taking much of the instruction count. And then there is a stack variable that was eliminated because we've seen that there is no push and pop that is being done in the after the optimization, because we are now simulating the register state at the register level. Then this is more still about the optimization that was done, and we've seen that the sign division had a very large binary before optimization, and after we optimized, because of the dead code elimination, it just become very small compared to what we had before the optimization, and this shows what benefits of implementing the optimization passes. And then the other, we've seen that we are testing the exit code, and for correctness of the output, then we do the instruction counts. So this is more of the design level that we did, implementing the test units, the unit test to verify that the iteration of what we are doing is correct, and the benchmarking script that is present in the source code. So we've seen that the register simulation caused a lot of instruction brought. Then there is the flags, the computational flags that are in x86. So they will generate actual additional comparison code, because we are simulating that as well. Then the system calls will introduce more of the instructions, because we are one system call from x86 will result into 5 to 8 inline assembly instruction for ARM-based ISA. Then we've seen that the optimization will reduce that brought, and the system call is something that we are not able to handle for now. So the overhead of system calls still persist even after the optimization passes. Then some of the challenges that faced during the implementation, we've seen that for now all registers map to I32 regardless the actual width, which is an ongoing improvement to make it time promotable modeling, because if you want to have fraud support and other various instructions, we have to avoid this 32-bit alloca. So it's an ongoing process. Then the cross-compilation workflow, for now, it is supported on we can build on x86 Linux, but the benchmarks run natively on the Mac OS. We tested on the Mac OS processor to have our output. So we are now having a modularized code generation backend. Yeah. So one of the challenging part was handling the indirect addressing mode during the register modeling before we generate the internal intermediate representation. Then the entry alloca, they are not promoted to by mem2leg, and this treats the roads as UB and eliminates the function bodies. We've seen that the entry block allocas will matter. They will not be promoted at the code generation stage. Then keeping verify module active, it catches the intermediate representation bugs and helps during the debugging and spotting the errors in the backend code elimination. So the future work is to support the floating point operations by refactoring the register model to a type parameterized allocation. Then benchmarking on the scientific kernels like dot product, matrix transpose, Fourier transformation functions as the primary HPC migration targets. Then testing on the spec benchmark, which is one of the rigorous TransISA evaluation. Then implementing the modular target system as discussed above to support different architecture. Rather than support for back OS, we can introduce RISC-V backend for code generation. Then implementing custom LLVM passes for optimization, like stack trimming, the flag elimination, to see if we can fix that issue that we've seen. Then x86 idiom recognition to the mapping that to the ARM sequence at the IR level before we pass those to the backend. Then the runtime and formal methods, we plan to leveraging the CMD by and translated SSE AVX code once the fraud register model is in place. Dynamic profiling, because for now the profiling that is being done is static one. We plan to have dynamic profiling. Then the formal equivalent translation, actually implementing proper-based testing to certify the semantic equivalent beyond the exit code checking. So we've seen that the correctness, we are now checking the output, the return status of the output code. We plan now to extend this to have a formal verification, property-based testing support. Then the conclusion is that the TransISA demonstrates a static source level transpiler built on the traditional compiler principles and can provide a viable way to migrate from x86 to ARM. The key contribution of this project is that we have a full pipeline that we can build on top of. Then we have configurable optimization passes. It is open source and it can be very easily extended. So by targeting the assembly source rather than binaries, the TransISA gives developers full control to inspect, verify, and tune their translation process. And this can be a sustainable tool for long-term software maintenance in the trending error. Yeah, that was it for my presentation. If you have any questions or discussion points on the project, feel free to share them with me.
Great. Thanks, Felix. So it looks like we're running a little behind, so we might have to hold off on questions. But yeah, feel free to reach out to him here. And yeah, great talk. Thank you. Next up, we have Andrew Espira, who will be talking about managing GPU clusters queues.
Hi, morning. So you can scan the demo so that you can have a view of what I'll be talking about. So I'll be ranting here while you have like a visual product view of how the intelligent can work within SLAM integration and all those platforms. So that's a live production system that's there. So you can just play around with it. So motivation, have you ever been at that point where you're like, oh, when is my job going to start? Or when is my job going to end on a cluster and stuff like that? And from an engineering point of view, like an on-call engineer, you're like, oh, all these GPU clusters, like thousands and thousands of hardware that you have to keep lookout for, and then you have all these scientists and researchers on your neck, like, oh, I submitted my
Oh boy!
I submitted my job 2 hours ago. It's like, oh, still in a pending state. I don't know what's happening. Yeah, there are amazing observability tools out there, but for you to get that real core value on how your GPU HPCs are working, you have to spend more money and a lot of money on them. So what I thought about from an SRE point of view, I was like, oh, what are some of the best ways we can find to allow institutions that have low cost to at least have a way to manage or have a visual view of GPU or their clusters. So I'm Andrew Espira. I'm currently undergrad. Not an undergrad. I'm graduate student at St. Peter's University. I'll be finishing up this spring. So let me see. So GPUs or HPCs cluster like a black box, and every black box leaves every on-call engineer in a way that you really don't want to be at this space when something fails or there's an issue and stuff like that. So every GPU cluster, every HPC clusters, you have the CPUs, you have the GPUs, you really need to have observability, you really need to have like all that metrics being pushed to the dashboards, and to have all these millions and thousands of dashboards that you have to keep your eyes on. And then you have also this other side of users who also want to know, oh, what's really happening with my job, what's really happening with whatever submission I've done on that cluster. And let me talk about a tool like SLAM. When you go to SQ, you submit your job, you are like, oh, you have all these SLAM templates you build, then you push a job on a cluster, and you're like, 2 hours later, the job is either in a pending state or the job is running, but it's running and it's a bit slower than you expected it to run before. And from a perspective of a user or a researcher or a scientist, is like, oh, SLAM is supposed to enable us manage the queue much better. As an engineer also, that's the point of having SLAM on our HPC cluster. That, oh, we can manage this queue, we can like distribute jobs much better using SLAM, but 80% of the time, that's not the case. So some of the questions like you get asked as an on-call engineer, why, when, and how, but you really don't have the answer. You can look at the distribution or the metrics and you see, oh, we have a problem somewhere here. We can do this. I can stop this job that's basically stuck on a queue. Probably it's more like memory or disk space and stuff like that. So we started working on this on a point of, can we get metrics from GPUs, HPCs that can allow us to build predictive or predictive models that can enhance like queue intelligence, more like queue depth and stuff like that, that can predict or offer insight into a scheduler on how efficiently jobs can be redistributed on a cluster, how efficient jobs can be run on a cluster, things like GPU pressure, bufferations, all this, you capture them, and then when someone wants to submit a job on a cluster, at least you get that insight of, if you submit right now, there's a lot of queue depth, or there's a lot of this, or memory pressure and stuff like that. Your job might take 2 or 3 minutes before it gets submitted on the cluster, and it might take like 4 hours to run based on the type of job you are running, an inference or something like that. So we are not building a scheduler. We are just adding insight, more like, we are giving more data back or insight into a scheduler that can allow that scheduler to work much better or much faster on a cluster. So what we did is like, building the model is not a big problem. Like, you have all this data, you have all these metrics, you can use all those type of modeling, you come up with all that thing. But then you are working with something that you want to give a user as accurate information as possible. Because if I tell you your job is going to take 2 minutes, then it takes 4 hours, that's a really drift that probably you not trust that insight anymore going forward. So we use calibration. So in this work, calibration matters more than the prediction. Like, if that model says 70%, your job is going to stay on the cluster for 2 hours before it gets submitted, will 70% of that time, that job stay on that cluster 2 hours? So if it doesn't meet that threshold, no, that's something that's really wrong. And we have an advisory threshold. So for each prediction that the model, so we use queue depth as the predictor. So each prediction the model gives, it has to meet certain threshold. If that threshold is not met within the barriers that we've set, that insight is not pushed to the user. It's basically blocked. So the cluster or the scheduler will now use telemetry data to technically just use pattern and telemetry data to offer insight to the user. So in terms of feature importance, so we did like queue depth as submit time. So one thing we were doing was more like, we wanted to find out, like, before a user submits a job, and when that job has been submitted on a cluster, and when that job is running on a cluster, those are like 3 different things, what state was that cluster before you submitted the job? What state is that cluster when you submit the job? And what state is that cluster after you submit the job? So all these gave different, you could see like, you submitted the job when we had like high memory pressure at that initial state, but then once that job got in the queue, the memory pressure had somehow dropped. So that changes also how your job is going to be run on the cluster, either faster or slower. And then, once that job gets into the queue again, someone else was also submitting the job at the same time. Now the memory pressure also increases. So that changes all those predictive factors. And then, so these are some of the results that we got. And from a reliability point of view, we more pushed all this work towards SLIs and SLOs, which are more like, you want to have all these indicators that can trigger an alert to an on-call engineer on how to probably re-provision a cluster or re-provision jobs on the cluster. And then we ran all these, the models on different EKS clusters and also on on-prem clusters. And when we kept on changing from probably SLAM, we changed from one GPU type to another. The model was the discrimination, like model transfer was a problem. So the model was performing better on one cluster environment, but then when you push it to a different cluster environment, it technically fails, or the prediction becomes like too poor for you to even make decision on that cluster. So cross-environment domain was or is a big challenge, and also cross-cluster domain also a big challenge. So what we did was more like we started detecting drift detection, and then from the drift detection we also capture like the ECE, MCC metrics and push back into the model that can allow that model to recalibrate on every new cluster or every new environment it's deployed on. So the thing was more like most of the time you'll want your administrator to technically fix jobs for you or things for you, but our assumption or our goal is more like we want to meet the researcher at their needs. You also have that ability to see, oh, let me submit my job at 10 p.m. because it looks like 10 p.m. is the best time to submit a job. Let me submit my job at 2 a.m. Looks like 2 a.m. is the best time to submit that job. And then these are like the design principles that we technically got out of the whole process of working with the project. So calibration of accuracy. Yeah, you can get the best prediction, 90% and all that, but at the end of the day, that model might as well not perform better on a different data set or this other data set that you get. And then minimal feature and maximum signal. So when we started, we looked for feature importance, like, oh, which features really matter? And then eventually, while we were going with the project, we now added Richert elementary data from DGMI. So if we talk about Q depth only predicts on or works better on how that job runs, but then there's now the hardware section. Oh, when GPU are on high temperature and stuff like that. And then so we can go. So when GPUs are on high temperature and stuff like that, so we added extra so I didn't add those slides there. So we added extra telemetry data like SMIs, DGMI metrics that now are more like predicting factors that are adding into the model, and this gives the model more data or more information about the hardware. And then you have this other side, you are predicting the job itself. And then so the other factor was more like, oh, a job might be stuck on a cluster not because you have less memory or the GPUs are being fully consumed, but just because, oh, a GPU is like the temperature high or the power is a bit low, stuff like that. So those are other factors that we are also using for recalibration of the model that now makes the whole insight evaluation into the user interface much advisory. So this is more of an advisory tool that we are pushing towards pushing into like a scheduler and things like that. Like, oh, in an AKS cluster, you want to add more pods, or when that cluster wants to add more pods, it has all these metrics and information that you can know when and when not to do all that information. So yeah, I think that's the end of my talk. And then the other thing is like, oh, if you look at the industry right now, NVIDIA purchased SLAM. So these are some of the features that they're bringing intelligence into Q schedulers. If you look at a company like CoreWave, they're really working towards making like intelligent schedulers. So you'll be paying a lot of money to have access to all this intelligence in schedulers and GPUs, because now this is more like the hot cake right now. Like, oh, having GPUs is like the core aspect of training models and all those other things. So yeah, So, any questions?
We have time for at least one question. Oh, yeah, go for it.
So what do you think about the impact of NVIDIA purchasing Slurm?
Yeah, I mean, like, for me, what I think is more like, it's more about you are going to pay. Right now, Slurm was more like supporting like institutions on open source basis, but technically we are going to get more features like intelligent queue devs, intelligent predicting jobs, which they'll technically force you to pay subscription for them and stuff like that. Because right now NVIDIA profit is more important than helping research, because everybody is fighting for that GPU space, everybody's fighting for controlling data centers and all those things. So yeah, that's why I feel like NVIDIA made that move. We need to take Slurm, or we need to take something out of the open source community and bring it in, or we will support some new features, but then the best features that we can give are going to be on a paid version or a paid something.
Thanks, Andrew. Next up, we have Michael Waxmonsky, who will talk about building stuff. So, yeah.
Is there control for the? Oh, it's fine. Okay, got it. Okay, cool. Awesome. All right. So so thank you, everyone. My name is Michael Waxmonsky. I'm a software engineer in the Applied Computational Sciences group here in Sizzle. And today we're going to be talking about CMake and incrementally transitioning your large model build systems to CMake. And we're going to do this in the context of my main project that I'm on, which is called Turbo. And no talk will be complete without a book of acronyms to throw at you. So Turbo stands for that. But basically what we're doing is we're trying to modify and enable the MOM6 ocean model to effectively use both CPU and GPUs, DOE systems, new NSF systems, etc. And we're doing that right now by leveraging a C++ project called AMREX, which stands for Adaptive Mesh Refinement at Exascale. It's one of the Exascale compute projects that came out of Lawrence Berkeley Laboratory. And so we're both working to modify the host model, and we're also working to modify the transition away from FMS to TIM. FMS being the flexible modeling system out of NOAA that they use in a bunch of their models. And TIM, or the turbo infrastructure for MOM, is the C++ AMREX equivalent. And so for the context of this talk, and we're also trying to create and verify current and new implementation via PF-unit, G-test, whatever we can use. So the context of this talk, we're going to try to focus on that last bullet point. So I just threw a bunch of words at you. I don't understand words. I like pictures. So this is the current setup that we have right now for MOM. So as you can see, we have our host model, MOM6. It relies on the FMS interface layer, and that's sort of the dividing line between the host model and the underlying FMS system that does sort of the heavy lifting of the model, and they use it through a bunch of different models. And so on the left is what we currently have. On the right is what we're trying to do. So, we have our driver, we have our TIM layer, and then there's our dependency on AMREX at the bottom there. And so before we start talking about CMake, let's take a look at what we currently have right now on the left. So if you look at the MOM6 build instructions, they support two different ways to build their software. One is with autoconf, and that's for the ocean only, so not really useful for us for an integrated build setup. The other option is their MKMF, or make file system. So that has not a super long process, but it's got a couple of things you have to do first. You have to create a text file with all the paths you want to compile. They have some utilities to do that for you, or you can do it manually. You then call their make file utility with the proper arguments, and then you can finally call make. But you have to do that for every single layer. So in this case, for mom, we have to do that 3 times. So again, I don't like words, I like pictures. So this is what one of these layers look like. So this is the very bottom of that dependency tree. So for this case, to build FMS, there's our call to list paths. So that's generating that text file for us. This is our call to make file, and these are all the arguments that you have to pass to it. Emphasis on the include and the link flags. We'll come back to those in a minute. Basically, for this process, you have to maintain those as you go up your dependency tree to your host model. And so maybe there's a way we can fix that and make that a little bit simpler for us. And then lastly, there's your call to make. Now, none of this is terrible to work with, but one of the things that we ran into was that when we're trying to add PF unit tests, the way that it worked with the build system, we just hit a lot of incompatibilities. And so we kind of had to make a decision, right? We could either modify the current build infrastructure to do what we needed to do. That has a fair bit of risk to it. There's a lot of uncertainty there. We know what we had to do today, but we don't know what we might run into next, and then the next thing and the next thing. It's also Perl and make files, which I'm not good at. If I'm modifying your Perl scripts, please stop me because there's a problem there. We also risk breaking our upstream community. I don't know what all they're using these tools for and how they're using them, so I risk breaking them unintentionally. We could completely rewrite the build system and make a completely new one in pure CMake. That is extremely time commitment. It's very invasive. It's not incremental. You have to do it all in one fell swoop. And it also requires pushing that dependency up to the mom community. And maybe they might not want that. There's actually a PR that was closed recently that did have a bunch of that. I'm not sure what the results of that PR was or why it wasn't merged in. So clearly that was not an option. So ultimately we went with a middle of the road approach, which is we will do what we can in pure CMake as much as possible, and we will own and we will take on the burden of maintaining that for the time being and see if we can sort of bridge these two worlds together. So first of all, what in the world is CMake? So in case you haven't used it before, it started back in 2000. It's sort of the fundamental code that came out of kitware and sort of made kitware. It started off as a simple build generator. So you had a high level abstraction and you just called into CMake and it generated your make files for you. As of today, it does way more than that. There's a very rich ecosystem within the CMake community that can do a lot more beyond even just building code. So I've been using CMake for many years, and so I kind of had in my head what I wanted this to look like. So, so this is about as simple as I could make this to do the very fundamentals of what we wanted to do. And so some of the main concepts here, within CMake, you're just calling functions. That's how you interact with CMake. That's how you tell it to do what you want it to do. Much like your software. You pass around, your variables, and you give it all these function calls, parameters. We'll see how this can get a little more useful and a little more dynamic later on. And the key thing about CMake is that it likes to, or it requires you to use targets for a lot of things. So in our case, targets are primarily going to be libraries and executables plus some other stuff. And we'll see what the other stuff is in the context of CMake in a minute. So just to see things side by side here, to see how things really link together. So on the left here is the exact same CMake file, and on the right is our PF unit file. And to walk through this a little bit, so the main advantage to using CMake is this find package call. I love using this because it gives me a lot of utility and a lot of tools for very little cost. And so PF unit, one of our dependencies, it gives us this add PF unit C-test. We'll talk about C-test later on in the slides. But basically, this does a lot of template stuff for us. It saves us a lot of headache from having to manually configure CMake to give us our unit tests. So obviously we have to tell it, hey, what are we compiling? And just like with regular Fortran code, you just have to tell it, hey, here's my Fortran code. And the key thing here is our dependency on that interface layer, that FMS or TIM layer. So in our source code, I'm relying on that interface layer. And notice on my CMake, there's nothing else. I'm just telling it I only want to care about the interface. I don't care about the other stuff. So how in the world do we do this? How do we define what that mom interface is? Because that's not been declared yet. So we're going to follow a pretty simple template here. So let's walk through this really quickly. So add library, this is sort of the main entry point to creating targets. There's add executable, that gives you a binary, but this is what declares the mom interface target name. I like to use prefixes, but you don't have to, so that's up to your preference. I'm telling it, hey, this is going to be a static library, so a .a file. I'm also telling it this is imported, because remember, we're not building this. This is outside of CMake. So we're telling it, don't build this, don't own this, just use it. So because it's imported, we have to tell it a little bit more about what that target is. So remember how I said earlier that targets are your binary or your library plus some extra stuff. This is some of that extra stuff. So I'm telling it that target has some additional properties that you need to know to use it. So in this case, I'm telling it, hey, here's where you find that library file. And I'm even telling it what the link language is. There's a whole backstory to that, but basically tell your CMake what your language is, please. I also have to tell it, where is my my module files or my header files? This is the exact same thing that we saw earlier, where we're passing around those header files and those include files. This is doing the same thing for us. And one of the key things here is the interface keyword. There's a couple of different options here, but this basically tells CMake, hey, whoever uses this target, pass along all this extra information, but don't make the user have to know about it. And we'll see what that looks like here in a minute. And then lastly, because again, that interface layer, it depends on my underlying implementation. So, if you're using FMS, it's going to depend on some other stuff. Sorry, if you're using the FMS interface, that's going to rely on FMS. If you're using the TIM interface, that's going to rely on TIM. But there's some other stuff there. So in our case, I'm just saying, hey, this is going to require an implementation layer. I didn't get in there then. Okay. So basically, here I'm declaring that there's a mom implementation layer, or target rather. So this 4 lines of CMake code, you basically have to repeat that for every layer of your dependency tree. And so we would do the exact same 4 lines for both FMS or TIM. We also need to do it for netcdf, because FMS relies on netcdf. So I pushed this all up and I said, hey, we're good to go. And then I got an email about an hour later saying, hey, we have a problem. So what's going on here? So I was doing all my testing on derecho. And in particular, I was using one of the older environments. I think it was like 23 or something like that. So a couple years old. And if you'll notice here, so this is the library directory for netcdf. And on derecho, we have our shared object files. It just so happened that our build process on derecho was linking against the shared object files. And so when I was building up my templates for all my dependencies for netcdf, I didn't use static libraries. I used a shared a target for that. And so I had hardcode .shared object file. And as we saw on one of our colleagues' local environments, they did not have that. And so this is one of the issues with doing this manually yourself, particularly with installed targets. You don't necessarily know what you're going to get if you don't own it. And so this is one of those cases where we had to make a decision. Do we force an update to an environment, potentially breaking something else? Do we pull in a copy of find netcdf? I know a couple of projects, they have their own find netcdf.cmake file. So I'm going to cheat a little bit here. And at the bottom of these lists, there's a package config directory. It doesn't look like a directory, but they are directories. I wonder if there's a way that we can leverage that. And the answer is yes. So CMake has the ability to interpret package config installs. And so there's a couple of extra things in here that we're going to kind of glance over for the moment. But the long story short is, if I don't want to have to own what my import looks like, and it provides a package config, all I need to do is tell it, hey, this is the name of the package config file, and CMake will handle the rest for me. There's an add library for an alias there. Again, this is all, this gets into the sort of the weeds of how to use CMake, but effectively it's just 2 lines of CMake to get that thing, and I can use that target just like I did earlier. And then again, we do the same thing for netcdf Fortran. It's a little bit weird because netcdf-C has a lib directory option, but netcdf Fortran does not. Maybe it's the version, I don't know, your mileage may vary. And so, so the key takeaway here is, what we did in 4 lines of code, it would actually blow up a little bit more in our face if we had to support static object, shared objects. You get into the weeds of supporting different user environments. It can get really complicated really quickly. So if you can, leverage your package manager as much as possible. And so at the end of the day, this is it. I added 1 additional line of CMake that said, hey, go find your dependencies and populate some targets for me. And I changed my target here to be my prefix name, but I could have left it the same and it would not have mattered. But this is the goal that we were trying to get to. I don't want to have to deal with, from my perspective, I don't want to have to deal with my upstream dependencies, transitive dependencies. I just want to depend on the thing that I care about the most, in this case, my interface. Everything else below it, I don't want to know. So some additional things that I've come across over the years. So every project that I've worked on has their own build infrastructure. They always say, oh, but we're doing something different. We're doing something unique, and we're doing it in a really weird place in our build system. Cool, add custom command. One of the things I didn't go into was that there are different phases to CMake builds. But there's different options here that you can use, and you can throw in this add custom command pretty much at any point. You have to do some additional logic to make sure that it triggers at the right time. But essentially, so long as you have a Python file, shell script, Perl script, you can just add custom command and it'll run that for you at the right time. Something I did not know until just this week when I was putting these together, one of the things I ran into myself on the CAM project was that we had an issue with the Intel LLVM compiler, and it wasn't vectorizing our code just right. And so I had to add an explicit line on our make file for Intel LLVM and this additional compiler flag for this file. And so I did some digging, and it turns out you can do this today in CMake as well with the set source files properties. We're getting into the weeds here of CMake a little bit with generating expressions and whatnot, but long story short, even individual files, you can specify individual compiler commands, and it will know where to, you have to do some additional setup to make sure that it follows the files correctly. But once you have it set up, so long as your target is referencing that file, the target will know, oh, this file needs to be built with this additional command line argument. And honestly, at the end of the day, just like I found out for the second point here, I don't like this. I hate that this is the way that it is, but the LLMs are really good. CMake is not new. It's been around for years. There's a lot of good CMake out there. There's a lot of not good CMake as well, but there's a lot of good CMake out there. And the LLMs are really good at pointing you in the right direction as to how to use it effectively. So, so to zoom out a little bit here, it's not just a matter of making our build simpler. You get some additional benefits by converting to CMake. One of the big things here, obviously we're trying to do some more unit testing. Because everything is all integrated into the CMake ecosystem, one of the things we get as an immediate benefit is C-test. And in this case, I actually didn't even really need to add the test directory. As long as I'm in the build directory and I call C-test, it'll just run every test that it finds. And I got that for free because I was leveraging what CMake and our CMake infrastructure provides. And lastly, so this one is a bit of a new one that's kind of scary to some folks. Because you're using CMake, you don't have to rely on make files. You can change out your build generator. It can be make files, it can be Ninja files, and as of, I think it's CMake 4.3, you can use fast build. They have different use cases and different scenarios where they benefit, but you don't have to rely on just make files. You can use other things and get some additional gains here, especially for large projects, as we see here for the LLVM project. This came from Kitware, so take their numbers for what they are. So in summary, you can isolate your dependencies manually. Ideally, you can use package config. If you can, use find package like we did for PF unit. But you want to try to isolate yourself as much as possible so everything downstream can use modern CMake. And then this way, you can start to incrementally convert anything downstream to use CMake. And now you can sort of have that discussion, how do we push this upstream? It does require changing your perspective a little bit. Will it do everything that your custom build infrastructure does? Probably not, but it probably has an alternative. And I want to emphasize, this is not the end goal, right? Like, we don't want this lying around for very long. Ultimately, what would be nice is if we could push this all upstream so that we can just call find package on our model, and that way we have our interface target. And I'm none the wiser. And thank you, and I'll take any questions.
We maybe have time for one really quick question. Otherwise, okay. Well, thank you, Michael. Yeah, gonna move on. Last one is Gaurav Vaidya talking about testing code that is big, slow, or non-reproducible. Certainly not my code, but thanks.
Hi, everybody. My name is Gaurav Vaidya. I'm from the Renaissance Computing Institute at the University of North Carolina. And I'll be talking about testing software that's not easy to test. As you might imagine, I'm interested in this because I have a piece of software that is not easy to test. And so the idea behind this talk, and I have a link up for slides if you want to take any of these URLs or you want to follow along. And my idea with the talk is I'm going to talk about what I did to test and validate a particular piece of software, the Babel pipeline, and its front ends, which are part of the NCAT's Biomedical Data Translator project. Excuse me. If you want to learn more about Babel itself and how it's structured and what it does, we have a preprint up on arXiv that we're hoping to get into publication soon. And if you want to learn more about Translator as an overall project, we have a publication about that came out last year. So I'm going to be talking about the lessons that I learned in this process. And at the end, the idea behind doing this talk is to try and get feedback on how you all test software that is difficult to test. So what makes scientific software easy to test? The ideal piece of software that we want to test is something that runs quickly, something that runs repeatably. It takes a small amount of resources, so you can test it on a laptop. You don't have to test it within a cluster or an HPC environment. And the data that you're using is small and is easy to share. Let me tell you about the Babel pipeline, which is none of those things. The problem that the Babel pipeline is intended to solve is that the biomedical data translator needs to harmonize biomedical concepts from different knowledge graphs. So if it picks up a knowledge graph from one source, it might see that water is referred to by a Kebi identifier, like 15377. From another source, the same water molecule would be referred to by a PubChem compound identifier, 962. From a third source, a Cas identifier, and so on. And we wanted to set up one place where you could take one of these identifiers and say, what is this really? And we would give you back a normalized identifier, which all of the different translator components could use. And then we would all be talking the same language and we could exchange data back and forth. So Babel is a human-curated pipeline for synthesizing these identifier cross-references. It generates outputs up to 23 different biomedical classes. I'll show you a breakdown of that in just a second, using 278 SnakeMake rules to create 490 million records for 637 million identifiers, which it brings in from 65 different identifier sources. So the data that's coming out of this is pretty big. In the current translator infrastructure, every time you ask translator a question, it needs to normalize information from these different sources. So we had to build a high-speed normalization service based on the Redis database, which returns a preferred identifier, a preferred label, and a standardized type from the BioLink model, as well as a list of all known equivalent identifiers. There's also a name resolver service, which can be used for entity name recognition. Within Translator, this is primarily used for running our autocomplete. So you go in and you start typing in the name of a disease that you're interested in, and we'll search in our database of diseases and give you back some options. So to give you a breakdown of what goes out in the Babel outputs, there's about 250 million protein identifiers that we produce. There's 108 million small molecules, 59-ish million genes, and then smaller and smaller and smaller categories, 37 million publications, and so on, all coming from a variety of sources. So let's see how Babel stacks up against our previous criteria for software that's easy to test. Runs quickly? No. The Babel pipeline takes about 20 to 30 hours. That could be improved, and I'm working on improving it now. It's not repeatable because it depends on upstream databases. Those upstream databases could change their formats. They could change what kind of information they're including. They could split up their inputs into smaller subsets, and then we have to choose which ones we want. Babel downloads 437 gigabytes of downloads, plus the data that's extracted from those downloads. And not all of these are versioned, so it can be difficult to tell when these have changed. Some of them are updated daily or weekly. Some of them are updated every couple of years. Takes a small amount of resources? Nope. Babel can take up to 500 gigabytes of memory for some of its slowest operations. You know, confession time, this is purely because we haven't really sat down and optimized it because we've had other stuff to work on. So that is something we can definitely improve, but it's always going to be hard to run something like Babel on a laptop, which is what would really make it easy to test. And finally, the data is small and shareable. Here we have one small win, which is that very little of our Babel data is something that can't be shared. We do have a lot of data that can't be distributed. The distinction I'm making there is we don't have anything like patient information or information that needs to be treated with a lot of secrecy. Like we can always take a subset of that data and make it available somewhere. But in general, we can't take an entire database and put it up within our share it ourselves. We always have to go back to the original data provider to get that information. We generate 48 gigabytes of intermediate data, which is mostly a list of identifiers and cross-references. And then we produce 20 gigs compressed of compendia files, which are all of these mappings saying these, here are all the different identifiers for water, and water should be considered a small molecule, and all that kind of information. And then 34 gigabytes compressed of synonym information. What are all the different names that we have for water? Finally, there's if we took all of the data that we have and put them into Apache Parquet files, which are easy to distribute and query, we get about 147 gigabytes. So that's, gives you everything that's going on in there, but it's difficult, again, to download, to work on locally, or to test outside of our HPC environment. So what are our testing goals? Why are we testing? Why do we test Babel? The first and probably most directly beneficial role is to detect errors early. We don't want to wait 12 hours and then have some kind of an error come up in our pipeline that we then have to fix. We don't have to rerun the whole pipeline because CMake can continue on from where it was previously, but it's still annoying to have to stop. The thing we really don't want to do is to build the whole thing, put it up on node norm, and then realize that we've missed out on 10 million identifiers because of a bug somewhere in our pipeline. So if we can catch that stuff before we start the pipeline, that makes everything run much more smoothly. We want to prevent regressions. People keep, with an output like Babel, which is really just a huge set of these cross-references, it's pretty rare for people to come to us and say, hey, I systematically looked through what you're doing, and your labels for one particular source all have weird characters in them. Can you go and figure out what you're doing wrong? What's much more common is that in the course of testing other parts of Translator, people will come to us and say, hey, there's these two identifiers. I think they should be considered the same thing. I don't know why you're splitting them, considering them to be different. Or vice versa. Here are, like within one, I'm seeing that you're normalizing this chemical into this other chemical, and that's incorrect. These are very different chemicals. We need to treat them separately. So we're getting all of these kind of point information on things that we're doing wrong. And when we fix those kinds of things, we want to be able to go back later and say, are they fixed in every future release? Have any of those bugs reappeared? Have we done something wrong? We want to prevent issues when different components are joined. This is not really a huge issue for Babel because it mostly we use our own internal formats, but it's only really like 2 internal formats that we use. So it's pretty uncommon for one component to produce something that another component then fails to read or reads incorrectly. And finally, to validate against benchmarks. So again, sometimes we're getting these point reports. Sometimes somebody does go in and test like 100 different chemicals and says, okay, I tested these 100 chemicals, 50 of them are great, 50 of them have problems. And then it's useful to be able to take that combined information and say, okay, how do we fix something? How are we doing against all of those 100 chemicals in the next release and in the release, in every subsequent release? And finally, we want to track known issues. We want to know what the, again, these individual bug reports that come in, we want to firstly validate them, make sure that they are, somebody maybe spots an error but tells us that it's in a different environment. So we want to make sure we are seeing exactly what they're seeing in that environment. And then we want to test it going forward. Did we fix it in the next release? Did we fix it in a subsequent release? Why don't we test? Well, the usual reasons not to test are things like it takes too long, both in terms of developer time as well as in terms of running the tests and then fixing things based on them. But quality is important, regressions are frustrating, and tests are important documentation of what the code is doing. And it takes away time that could be better spent on programming, but it's important to balance features, bug fixes, tests, and documentation. All right. So this is sort of a high-level overview of Babel and how Babel is structured, where we have kind of downloaders doing ETL on different resources. They build a bunch of cross-references. A compendium builder combines those cross-references, builds these sets of equivalent identifiers. Those go into a Redis database for node norm, and then into an Apache Solr database for the name resolver. To begin with, this was sort of the system that was handed to me in 2021, and I was like, how am I going to test this? These intermediate files are huge. There's so much churn going on between these different versions. So I started off just by testing the endpoints right at the end. Those are already up in databases, so they're super easy to query. They have fixed APIs, so I can just use those APIs. Send message, send an identifier, see what it gets back, check if that's what I expected or not. The next thing I did was to take those massive output files and put them into Parquet database files using the DuckDB database system, which is a column-based system, which means it's easy to run, or it's fast to run, or efficient to run aggregated queries across it. So rather than saying, give me, what identifier does X resolve to, it's really good at answering questions like, show me how many identifiers I have that are showing up in multiple data sets, or show me how many identifiers I have that have the exact same label between them. So that was my next step of doing testing. And now I'm coming back and working on those individual pipelines. And I'll talk a bit more about that in just a sec. Okay, So you'll notice the layers in my presentation are out of order because I really wanted to tell you the story of how I built up the system that I'm describing here. Right at the end, I have like one slide where you'll see the layers in the right order. But to begin with, I started with testable issues. So as I said, this confirms issues that people have already raised, and it's important to track when those issues reappear in the future. So for this, I built a nice validator. I built it in its own repository because I didn't want to mess anything up with the Babel source code itself. It works with PyTest, so you can choose individual test files to run. You can choose categories of tests that you want to focus on, and then everything else gets skipped. You can choose which deployment to test. So whether you're testing in our development environment, or if you're testing in our CI environment, or on production, you can kind of test whichever one you want to, which is great when a new deployment gets sent out there, and then you can run the test and say, all right, it looks like everything is up and running. You can also mark tests as not expected to pass, which, my goal here is to absorb everything that people are sending me, and if there's a at least initially, everything they're reporting me are tests that will fail, and then hopefully we'll get more and more of them passing with time. Now, initially, I was thinking maybe I need to store this in a text file or a CSV file or a TOML file or something like that. But then I figured it would be easier to put it all into a Google spreadsheet, because then I can, it's easy for me to add a bunch of tests all at once. It's easy for me to look at what all the tests are doing or to edit them. And since this is a world-readable Google spreadsheet, it's something the testing software can just download, generate tests based on that, and then tell me, here are the tests we're skipping, here's what's passing, here's what's failing, which is pretty cool. For each failed test, it'll give me like detailed information saying this is, the test says when you normalize this identifier, you expect to get this, but actually you're ending up with that. Here's the difference. Here are the different BioLink categories. Just gives me any useful debugging information. Like I said, initially I expect just about all of these tests to fail. So I have kind of flags in this file where I can say, yes, this looks like something that's, that is currently passing. This is something that I'm not expecting to pass. And because of the way that PyTest works, anytime it encounters a test it expects to pass in strict mode, it will then tell me, hey, there's a test here that you haven't marked as passing, but it isn't actually passing now. So now I know to go into my spreadsheet and put a Y into the right column. Now, one problem with this approach is that the spreadsheet can be difficult to maintain. I was kind of hoping that this would be something I could share with the other people at Translator, which, I didn't do the effort to really get a lot of people involved in this, but it was kind of extra work on their part. So the idea that I'm currently working on is to incorporate these tests directly into GitHub issues, so that when somebody submits a GitHub issue, they can put in a little bit of text like this, which is directly inspired from Wikipedia's syntax, and test. And if I see an issue in GitHub and the issue has been closed, I assume that that test is expected to pass. And if it doesn't, I can provide an error message and say, hey, there's a failing test here. And if the issue is still open, I can assume that it's expected to fail. And again, if you have an issue where all of the tests are passing, but the issue is still open, I can put that up as a reminder to say, hey, go back, check that issue out again. Maybe it's time to close it. So this is what it kind of looks like on GitHub itself. There's also a YAML-based syntax that I put in there, so you can put like a whole bunch of identifiers if you want to test that. And yeah, when you run this again as part of that same testing infrastructure I just described. So again, you can choose which environment you're running these tests again. You can choose which test to run, and that'll tell you which issues are in the wrong status and that you might potentially want to change. So the next thing I did after looking at the sort of individual point tests is to look at comparative tests. So even before I go into like what is actually in this file, is this identifier there, is this identifier not there, I can do these very gross comparisons and just say, okay, when you have a set of inputs, so in our 2025 September release, we had 688 million identifiers. In the 2025 November release, we have 637 million identifiers. And then it breaks it down by biolink type and tells me what the differences are. And you can kind of see right at the top, there's already like a 7% difference for that release. There's a 10% difference for the number of cliques, which is huge. So clearly something is going wrong. And this is something you can also break down further, where you can break it down by individual prefixes. And that kind of immediately points us on that first row to saying, okay, uniprot KB identifiers have unexpectedly we've unexpectedly lost 54 million of them. So now I know immediately where in my code to go and look at stuff. Naturally, we want those basic testing layers as well, just pure unit tests, which run quickly, which run on every pull request. We usually use mock objects or sample data to make sure that just the logic of the code is working properly. The thing I'm currently working on is what I call pipeline or partial tests, where rather than running through that entire system all the way to the end, which takes a lot of memory, I just run the parts of CMake that download a single file, extract all the information out of it, and then I can do validation on those outputs. Like, did I get more than 10,000 cross-references from a particular source? And if not, I get a report from my test system saying something is wrong. This does take a while to run, but you can use PyTest. The PyTest system is pretty good at allowing you to define options to say, okay, don't run this by default unless I specifically tell you to run these pipeline tests. And then there's unit tests for individual front ends, which kind of do what you would expect, where we have small sample data files. They get loaded into a Docker image, which replicates what the actual database backend is going to be, runs a whole bunch, sets the front end up to point at that database, and then runs a whole bunch of tests against that front end. There you go. Finally, the best thing we get out of those DB databases is this ability to run these big aggregation queries, where we can ask it things like, is the same identifier appearing in multiple places? So that's those are databases we generate as part of the build process now. So that's something that's easy for us to download and query. So yeah, so in summary, we started with unit tests, then moved on to functional tests of the front end, then comparative tests so I could track changes between them, and then functional tests within the individual pipeline. And that's how I kind of broke down this big problem. Here's like a table with just all of the testing layers, if that's something you're interested in. And sort of the lessons learned from this. You don't need one sophisticated comprehensive testing regime. Just whatever testing methods you use is better than nothing. If you have multiple components, think about how you can test them individually, together, as a developer, as a user, and so on. A single test is far, far better than none at all, and will make writing the next test after that much easier. Test as often as you can, before coding, after coding, before deployment, after deployment. And there's lots of sophisticated testing systems. We just saw Julian yesterday. LLMs can really help with writing tests, with evaluating what is covered. And if you're lacking time, think about how to involve your users in debugging and testing. All right, thanks so much. I have like a request for feedback. If you all have ideas on how I can test my software better, how you're testing software like this. The ucar-sea organization has a public Slack that any member can join, and anyone can join ucar-sea for free. And they have a testing working group. So that's a great place to meet other people interested in testing, see presentations like this, and see what everyone else is doing. So that'll just leave the acknowledgements up. Does anyone have any questions?
Any quick questions? Cool.
Yeah, I'm also here for the rest of the day if you want to meet up.
Cool. Awesome. Great. Thanks.
Thank you.
Yep. And so right now is a break, so you can grab any of the speakers here to chat, and we'll come back at 10:20 for the next and final round of talks. Great. Thank you all.
Okay, so I think we're going to get started with our final session of the conference. So thanks again to everyone for being here and participating. And so our first talk of the session is going to be Alex Richert with their presentation, Continuous Integration Workflow Improvements at NOAA EMC.
All right, hopefully you can see my screen and hear me okay.
Yes, we can.
Great, thank you. Okay, good morning. I'm Alex Richert. I'm going to talk about, well, first, I'm a contractor at the NOAA Environmental Modeling Center. So today I'm going to talk about some of the improvements we've made in our continuous integration at NOAA EMC in the last year or two, and just talk about some of the particular kind of tools and approaches that have been useful to us in our software development and modernization journey. So first I'll talk about how we have simplified and consolidated a lot of our continuous integration code using reusable logic. I'll talk about how we have integrated SPAC into some of our CI workflows, including I'll talk about what SPAC is if you're not already familiar with it. And ultimately, that will build up to talking about how we have accelerated and intend to further accelerate development by pre-building CI dependencies, which turns out to be certainly not the only, but a significant bottleneck in terms of our CI workflows. So I want to start off by talking about GitHub custom actions. So basically, all of our codes are on GitHub. So a lot of what I'll say will probably apply indirectly to GitLab or other services which may have equivalent offerings, but I'm going to basically talk about things in a GitHub context. So within GitHub Actions, which is GitHub's CI offering, there is a feature called Custom Actions where you can write your own, and basically you can write your same piece of CI code once and then use it over and over, including across repositories if you want to. So a custom action, again, is just a reusable bundle of GitHub Actions code. There are a few ways that they can be written. I've mostly found the sort of YAML formatted files to be the easiest to work with and the most useful. So if you're familiar with GitHub Actions files and the way that they're that the YAML definitions are laid out, if you look at a custom action, it's going to look very much like that. Typically, a custom action will live in a dedicated repository, but it doesn't have to. You can also do clever things like if you have 10 CI workflows in your GitHub repository, and also you have certain logic for like installing dependencies or doing testing or whatever that you're using over and over across your workflows, then you could also have a custom action that just lives within that repository and is used by workflows within that repository. So there's a fair bit of flexibility there in terms of how you can use them. So custom actions, again, allow CI logic to be modularized and reused across repos, and it basically runs, with some caveats, it basically runs in the context of the calling workflow. So it might be it may either be helpful or confusing to say that I consider it sort of analogous to sourcing a shell script in that it is, running within that same context where you're calling it. So it has access to the same file system when you run your custom action from whatever CI workflow is calling it. You can modify the shell environment by updating the GitHub end file from your custom action, and then you still have access to other actions, including the GitHub published ones. So many of our custom actions within them will use GitHub caching functionality, artifacts, and just miscellaneous other actions. I guess one immediate consequence of that is that it's important to be cognizant of security. It is possible if you use a third-party custom action that somebody could put malicious code there and try to exfiltrate your API keys, or if you have it tied into deployments, then somebody could if you're deploying documentation or deploying to a website, then an action could get in there and modify that. So you want to be careful of what they use. So this talk isn't about security, but since I'm talking about GitHub Actions, I wanted to just call attention to some of the security settings that are available under GitHub Actions. So if you go into your repositories, for the repository where you are actually calling or intend to call any actions from, there's some settings you can use to kind of lock things down a bit. So you can limit where custom actions come from. So that would, for example, keep some previously unknown developer from coming along and putting in a PR and running your CI workflows with some malicious or questionable third-party action. So you can lock down what's actually allowed to get used. And though it's not something that we do at EMC yet, it's generally considered best practice to specify a full-length commit hash when you point to a custom action. So when you invoke a custom action, typically you would just do, basically you point to a GitHub repository and then some reference for it. So a tag, a branch, whatever. And it's generally considered best practice to use a commit hash, so that way you know exactly what code you're getting, and a malicious developer can't come along and retag a version out from under you. Anyway, enough about that. So as far as why we use custom actions, this is kind of a motivating example, and what initially got me into getting interested in applying GitHub Actions or GitHub Custom Actions is just that we had a lot of reused code. We had a lot of copied and pasted code, a lot of redundancy. So on the left here is just an example from our G2 library, which is a GRIB2 library. And we had probably about 100 lines of code for checking out each dependency, seeing if we had the build already cached, and then doing the build itself with CMake or Auto Tools or whatever. Now all of that can be condensed down into within that workflow, within the G2 CI. It ends up being what we see on the right here. So it's just, less than 10 lines of code to basically accomplish the same thing. So all of those repeated steps that we were doing before are abstracted into this one custom action, so that when we need to make updates and so on, we can just do that all in one place. So it makes our CI code a lot simpler. So that's what developers, if there's a CI failure or something like that, that's usually what they'll be interacting with. So it simplifies that and just consolidates the logic. So it really reduces the maintenance burden by a lot. And so, so especially when we don't have, we don't have a big team to work on these things. So consolidation and making the maintenance easier is really valuable to us. So I'll just kind of give an overview of some of the things that we have custom actions for. One is installing and running unit tests for a given package through SPAC. So we use that for workflows, some of the workflows in our libraries, as well as one or two model codes, including UFS weather model. So it will basically take the modified code, or it gives you the option of taking the modified code and building it through the SPAC package manager, which again, I'll talk in a few minutes about what that actually is if you're not familiar. We have a custom action for installing the Intel toolkit, so compilers and libraries, including automatic caching in the GitHub Actions cache, because that was another pain point where we had a lot of copied and pasted code in our CI, and then when something needed to get fixed, it had to then get fixed across 5 or 10 or 15 repos, and that's no fun. We have a custom action for building and deploying C-Dash dashboards. If you're not familiar with C-Dash, it's basically part of the CMake C-Test ecosystem from Kitware, and it basically provides you a really easy way to generate and push dashboards that track code health, so things like code test coverage, number of errors and warnings during configuration and build time. You can have it run Valgrind to do memory checking, this sort of thing. Anyway, really handy tool. I suggest checking it out if you develop and release software. So we have a custom action for generating those dashboards because all of our code is already in CMake, so it made the integration there pretty easy. We have a couple of actions related to what I showed on the previous slide, where we basically took all of our repetitive CMake or Auto Tools configurations and builds, and it just kind of put that all into one place, so we can build a kind of a dedicated, or have a dedicated system for building the dependencies for our libraries. And then I also generated an experimental custom action for doing AI LLM-based code reviews. So my prediction as we go forward is that these three that I've dimmed here, the Intel, the CMake, and the LLM code reviews, will probably go away or significantly transform in some way. For the Intel ones, as we move more toward using containers in CI, which I'll talk about in a couple minutes, I think we'll probably be able to use the Intel published container images there. And so I don't think we'll need to maintain our own action there. As far as the CMake one, I'd like us to move over to, or I plan to move over to just using SPAC to build everything out in an automated way, hopefully into container images, which again, I'll come back to. And then I think we, at this point, have better tools available for doing the code reviews. But I think the SPAC-based builds and the C- dashboards, those will probably evolve over time, but I anticipate that we'll keep those in some form. Okay, so finally, I'll talk about what SPAC is and a bit more about how we use it in our CI. So SPAC is a package manager. It basically came out of the kind of scientific HPC context where you had long chains of potentially complex software interdependencies, and so it's built to handle those. The kind of defining feature of SPAC is its concretizer, which is just the SPAC way of saying the solver. So it uses a directed acyclic graph concept to model dependencies between software, to capture dependencies based on versions or version ranges, build options, this sort of thing. So it's very flexible, and it is, if not the most popular, probably one of the most popular kind of configuration as code oriented package managers. So you can do everything through YAML, and it's not language specific compared with what are probably in reality otherwise more popular package managers. So SPAC comes out of the national lab space, so it's pretty widely used there. It's used a lot in academia. It's used a lot on HPC systems and in some parts of industry. So in the CI context, SPAC helps us to configure our software dependencies in a pretty nice, maintainable, machine-readable way, and then we can store those builds for reuse in order to speed up our workflows. Just as a side note on SPAC and the way packages are built, each SPAC buildable package essentially has a recipe called package.py, and in my experience, the health and robustness of that recipe greatly benefit from developers maintaining those recipes. So if you release software that's used, especially if you release software that's used outside your team, I would really suggest and urge you to consider maintaining your code SPAC recipe. So SPAC does have a couple of rough edges. There are a few things that it doesn't do out of the box. So I've also written a SPAC extension, which is basically just a set of custom commands. I'm not really going to go into detail here, but again, just to say that some of the things that SPAC doesn't do right out of the box, we do through our custom extension. And then actually, I think I also have a custom action for tapping into that, so we can access that in our CI, as well as using it in some HPC contexts. Okay, so to further motivate the problem on trying to speed up our CI workflows and dependency builds, some of our workflows can take 30 or 60 or 90 minutes just to build the dependencies, to say nothing of building and testing the code itself. So there are a few ways that we can use SPAC to build out those dependencies for reuse later. We can save a whole installation path to a GitHub Actions cache. It's a little bit less flexible of a solution because if something changes, like we want a new version, then we end up rebuilding everything. But it's a pretty good solution, and it saves us a lot of time. We can also save each package to a SPAC-generated build cache. That can be a little more persnickety as far as reuse later, but it tends to speed things up while also giving us flexibility when we do want new versions. And then where I would ultimately like for us to go, and what we're working on and will be working on in coming months, is basically just baking everything into one container image with all the dependencies pre-bundled, but also with the ability to customize package versions as needed. So in terms of what I see as kind of the desirability or benefit of each of these, I would consider that to be kind of the ultimate goal here. So just in the interests of time, I think I will not go into too much detail here, other than to say that for some of our current workflows, we have a couple of approaches for caching our builds implemented. So each time one of our libraries, let's say, runs a CI workflow using SPAC, then it can, whatever packages that it didn't already have available to it, that it needed to build through SPAC, it'll automatically propagate those into the build cache, and then it can also tap into this common build cache that we've deployed that is basically there to provide pre-built packages for all of our repositories. So in many cases, our CI workflows can use partially or entirely those pre-built packages and not have to do it as part of their own CI workflows. So again, I won't go too much into the details here, other than just to say that when we do these SPAC-based builds in the common build cache, we can build individual packages, and SPAC will nicely bundle those up as essentially tiny container images, which we can then push to. In our case, we use GitHub packages, but you could also use Docker.io or other OCI services. And then we're in the process of implementing monolithic container image builds. And then in both cases, the idea is that in our CI workflows for a given library or WGroup2, UFS weather model, you name it, then they can pull in either the individual packages or ultimately where I'd like us to go is container-oriented builds. So what I see as the future is having one pre-built Docker image that has compilers, dependency packages, potentially even some test data. We can still make optional modifications via SPAC within that container instance, and then we build and unit test whatever the code is that we are testing in our CI, either through SPAC or CMake. So in principle, we could further clean up our CI workflows to look something like this, where basically we tap into the container image, make any customizations needed, and then do the build and test. So I think there's a lot of room for further consolidating the logic that we have and simplifying things and making things more uniform across our workflows, ultimately with the goal of supporting developers. So I think I will go ahead and stop there, since I don't think I have anything too new to say on my conclusion slide, other than to say that, of course, where this is all going is to make our CI workflows help them enable a more rapid iterative development cycle, so developers don't have to wait for hours to see whether the unit tests are going to run. So that's the ultimate goal here. So I will stop there, and I hope we will have a minute for questions. Thanks.
Alex, we do have a minute for questions.
Great.
Hi, Alex. Good talk. I think at the end you mentioned, you're at least building the whole UFS weather model. Are you doing any other kind of testing with the full thing on GitHub Actions, or is it just like the build test, like just making sure it works with compilers and everything?
Yeah, good question. Right now, it's just the build test. So basically, we have a SPAC package recipe built for UFS weather model. So it's using that to basically just get the dependencies, build the model itself in a couple of configurations, but that's the extent of the test, yeah.
Cool, thanks.
Looks like there are no more questions in the room. So thanks again, Alex, for the great talk.
Thank you.
So our next speaker is Kevin Hrpcek with a presentation embracing cloud-native CI and CD in research environments.
That's the next one. Cool. Okay, so I'm Kevin. I'm work on the Sizzle here at NCAR. I'm the internal cloud team, and today I'm going to probably ramble on, hopefully coherently, about cloud native CI/CD. There's a lot of topics in here that each slide could be like its own 10, 15-minute presentation, so this is pretty high level. All right, so problems in software dev, research environments, in the world in general. It works, a lot of times you have problems where it works only in a specific environment. You know, it's like, it works on my laptop, or hey, my supercomputer, but not somebody else's. Things are hard to reproduce, and reproducibility is important in the research environment. So SPAC, Conda, LMOD, they all do a great job, but they also only do so much because there's OS level dependencies and other things involved. Redundancy is often lacking in traditional ways of doing things with software dev and deploying applications onto single servers. Things are hard to update. Like, have you ever managed a server and like have multiple applications on it, and then you just get stuck into dependency problems? One thing depends on one thing depends on the version of another thing. Things don't work. Nobody likes manually deploying things either. It's inefficient, things break, unless you have it well documented, which honestly nobody does. It's different every time, and if you don't do it every week, then you forget how to do it. And then another big thing that people really don't think about probably too much is like, there's a bit of cultural resistance to moving to new methods and technologies for stuff. There's a bit of like, well, we've been doing it this way for so long, let's keep doing it. Like, POSIX is great, we keep using POSIX. No, don't keep using POSIX, you know. There's better ways. We need to be embracing these as software developers, and we're trying to modernize things a bit. So the base of cloud native is kind of like in containers, and I'll better define that in a minute, but like, why containers? You know, I realize this first bullet point is wrong because technically you can have Windows containers and Mac containers these days, but if it runs on a system, you can put it in a container in a self-contained environment with all your dependencies into one image that is portable. It completely detaches your application from the hardware and operating systems that are available. It's reproducible and archivable. Like, it's built from a spec file. You know exactly what's going into it. You can control what's going into it. You can put SPAC into it, or, you know, Conda into it if you want. And then the reproducibility is like, you have the same file with version locks, and it's the same every time. It's a single image file for your entire environment that you can archive in an image repository somewhere, and it helps reduce environment drift. You know, if it's built from a spec, if you're ever sharing a server with other people, things drift. Like, who knows what your colleague is doing on that server for updating things for their own application, and you never know exactly what is there. They also allow for quick scalability. If you need more instances of an application, great, just run more containers, and then load balance between them. It's super simple. In the back end, even if you don't know you're using it, you're probably using containers for automated testing through GitHub and GitLab or whatever your CI tools are. And the big ones in the space are Podman, Apptainer / Singularity, and Docker. So
let's get into this whole cloud native thing. It's a methodology of, development basically. And to be very clear, when I say cloud native, I don't mean it requires the actual cloud, like AWS, Azure, Google, whoever. What this really is a methodology. You can do cloud native development completely on your laptop with no external connections, And if you ever heard the buzzword serverless, that's kind of what we're kind of talking about here. It offers instant scalability with internal load balancing. You can, just by changing a single value, you can run multiple, it'll automatically spawn new containers of your application and load balance between them, and it's awesome. Instant failover. HA kind of comes with cloud. That doesn't work when you're just doing it on your laptop, but like if you're using like internal cloud stuff like NCAR, like even there, when nodes die or we do reboots or whatever, things just instantly fail over to other nodes. You no longer have to manage your own like supervisor D process for Python processes or your own systemd unit files to keep things running. Something goes down, it automatically comes up somewhere else. And in theory, that shouldn't be a problem anyways, because if you run multiple replicas and it's automatically load balancing between them, if one goes down, all the traffic just automatically goes to the other one while the other one comes up. So like HA is kind of one of the core things at the whole cloud native idea. Rolling updates and rollbacks. It's a container image. All you have to do is swap out the image that you're running and you're instantly running your older version. And these cloud native technologies allow you to define how things are rolled out, your updates. You can do very easy blue-green deployments where maybe half of your containers running your app start up running a new web application, new version, and then for a day you run the old version, new version side by side. It makes it super easy to do stuff like that. And you can easily piece together applications. You've also probably heard microservices and context with cloud stuff. It's really about breaking things up into smaller pieces, smaller containers. They're easier to manage, easier to update, and there's so many off-the-shelf options now. Every open source project has a fully supported official container image of their application. You need a RabbitMQ server, you just go pull down the official one. You need a web server, you pull down the official one, and then modify it with whatever you need to put in it. If you're building a Node.js app, you just pull the official one and throw your stuff into it, build it, and you have a great environment that's, I don't want to say supported, you could get support for them, but it's a standard environment. And another really awesome thing is offloading parts of applications to managed services in the cloud. And we'll touch more on that later, because you can manage things yourself, but a lot of it, the idea of cloud native is taking advantage of stuff that like my team manages for you or AWS manages for you. Another aspect of this is getting into like GitOps. Maybe some of you've heard this before, maybe not, but it's the idea of Git is and this could be GitHub, GitLab, whatever. Git is your single source of truth for your infrastructure or application itself. To make changes to for our internal cloud infrastructure is almost completely controlled by Git. We make changes in Git, we commit it, and then our CD continuous delivery tools automatically sync that back into our clusters, every whatever X minutes you have it set up to. And this can be expanded out to tons of different applications. It really depends on what it is and how it can benefit kind of like what you're doing for your research applications. It also allows for auditability and quick rollbacks. With Git, obviously it's very auditable. Everything goes into a commit. It's in there forever unless you delete the entire repo. But it also allows, as I mentioned before, with rollbacks, all you have to do with a CD tool is say, okay, go back to commit shot, whatever, or whatever tag, and within minutes, your whole app can be redeployed running an old version. And that's assuming you didn't do any crazy database schema updates that weren't backwards compatible. And I also kind of mentioned like scaling applications by changing the single value. And this kind of diagram is just kind of showing on the left. You know, you have your configurations for app and infrastructure, you have Git, and then you have your operator and configuration. It's Argo CD is what it's called. And then that's controlling how your clusters run and the infrastructure and applications themselves. Reproducibility, I've kind of talked about this already. You know, everything's version controlled is great, but containers package everything together into one thing. You build dependencies, your code, your runtime dependencies, everything can be packaged, and that's brings in like so much portability for like if you want to do testing. You built it here, but your colleagues at whatever university you can just send them the container image and they can do the same thing there. They don't have to build environments. They don't have to talk to their admins to get SPAC things added or new versions of whatever. Everything is contained in the image, and it can be up and running, you know, testing your latest model development in minutes. And another really nice fact about this is like all that the build information is very easy to save the output of it into like artifacts and CI. Because we need to know what is going into these environments, and that can be saved forever. CI and testing, test your code, come on please. There's no reason, there's no reason not to. GitHub Lab, everything makes it so easy. Like do some basic unit tests on every push. Nobody likes writing tests. LLMs are great at it these days. Send it your methods and just have it write some tests for you. On top of that, like just very simple linting and formatting. Some of that can be better as like pre-commit hooks in Git, so that way you're not like committing your badly formatted code and then having to recommit again. It'd be great if to not just do that in the first place, but you can still do that. And like there's really other cool things we're starting to be able to do with like you can do LLMs reviewing your code after it's tested and, you know, looking for bugs in what you've done or whatever, having a report written about your commits. I haven't really done that personally yet, but like it's a cool idea. And then on top of that, full application testing. These days, there's a lot of resources out there to do testing, and it gets really complicated really fast, especially in like this type of research environment, because you have, let's say you have 4 different compilers, 3 or 4, you have 3 OSs like Alma, Debian, SUSE, you have 2 different versions of those, you have CPU only, AMD, ROCm, and CUDA. Like you can easily run into like, you know, you need to build and test 30 plus different configurations of all that together. And no, that would be absolutely awful to do by hand. But if you're doing your CI correctly, it takes some startup time to get that all written. I'm not going to lie to you. Like it takes effort, but at the end of the day, you can run all that. You do a commit, it just happens. Or you do a tag push. Whenever you want to do those ones, it happens. And then, you know, you come back an hour later and you can view what failed, what isn't working. And that's just the build portion of it as well. Like once you get into, like, you want to test your model. Great, you build all these different configurations into different containers, and then you have to test all 30 of those containers with your model as well. And at that point, you just, you know, there's no reason not to. Do a comparison, you know, have your gold standard of your output that you're expecting, and then, you know, run your model through, test it with the output, see how it compares. If it's within whatever percentage that you feel is comfortable with, you can have a test pass or fail. And with all this, if like, you know, using CD, your updates are live within minutes of a Git push, if that's the type of application you have. And POSIX. POSIX is overrated. There's better stuff now. Like it has its uses. I've used it in HTC environments before, and along with POSIX, along with object storage. But like it's great for scratch space and software storage. It's fantastic. It'll be useful for that forever. But for everything else, like objects, like it's great for your inputs and outputs in an HTC or HPC environment. And there's so many cool things you can do. You can, you know, when an object is put into a bucket, created, deleted, whatever, you know, you can send an automatic message to Kafka or AMQP broker based on that. You can do S3 select, which is like you can actually query your JSON, Parquet, or CSV files directly with like an SQL query in your request to your object. That's pretty cool. Then there's also more things coming along, like, you know, Zar's been around for a while, which is your cloud native n-dimensional array format. Kerchunk is kind of trying to be Zara, but for your old school NetCDF, HDF objects. And it still offers like so many functionalities of POSIX as well. You can do your byte offset reads. You don't have to pull down a full object every time you want to do it, or partial overwrites as well. Bucket policies easily replace POSIX permissions, and they're probably more flexible. And bucket lifecycling, you can also do really cool like tiering of your data. If there's some certain amount of time, it gets moved somewhere to cheaper storage. There's also really like you can do bucket mirroring, like remirror between different sites at NCAR-ish S3 option, one of them. Functions as a service. These are pretty cool. If you haven't heard of these are, if you've maybe heard of AWS Lambdas, but it's like decoupling specific functions from an application, basically through a simple HTTP call to some API endpoint in the cloud. And like, you know, you can just offload, maybe you have some heavyweight CPU, heavy like NumPy, plotting, whatever functions in the application that you want to keep the application lightweight, or you don't want to bother with parallelizing it within the application. Cool, send off 1,000 of these to a function as a service thing. It does it all, and it returns it to your application in time. And like, you know, these can scale to thousands. AWS will tell you millions of functions if you run it on there. But it's really useful for doing stuff like if you have a web UI doing live analysis of, you know, outputs. You can have a simple lightweight web UI that calls function as a service to, you know, plot your data file and, you know, or do something to it and, you know, return it. It also, you know, if you do want to do really lightweight analysis on your laptop to visualize things, great. You know, send off all your heavyweight functions to a remote provider to do it all. And, you know, there's some playing around with doing like model inference inside functions as well as these days. No talk is complete without AI. AI in the cloud is kind of a good, cloud natively is kind of a good fit. You know, most of it uses object storage these days. And almost all the tooling is built into like cloud environments, like the RAG stuff, MLflow, Kubeflow, basically managing like model life cycles from start to finish, and then, you know, deleting it at the end because you realize it's trash. Kubernetes is largely used for ML training these days, but I'm saying with a caveat, like I am like, you know, let's make good use of our resources, and in environments where we have a supercomputer that has 350 whatever A100s, like it does make sense to continue to use that for like any ML training. Maybe there's a day where it doesn't make sense to, but like I'm all for making better use of our current existing resources. And other awesome things, you know, you can self-host LLMs in your own Kubernetes environment. We're playing with that here at NCAR. Hopefully going to roll something out where people can have a coding-focused local LLM, so you aren't uploading your API keys, passwords, and stuff into Google Cloud and whoever else who say they're not doing naughty things with them, but they probably are. And like, you know, containers also allow for just quick testing of CUDA, ROCm, whatever versions of stuff in AI environments. So this is just, I wanted to touch on, you know, a message-based workflow, very cloudy-like. You could do this on servers. People are doing this on servers. I've done it on that. But like in a cloud environment, like, so let's say at the bottom, I don't know how this pointer works, whatever. You have a process that's ingesting data. And let's imagine this is all in the cloud. A process that's ingesting raw data that you need to do some processing on. Great, you run that as a container in your cloud native environment. It uploads a bucket into S3 that is also local, not AWS S3. That's just a compatibility thing. And then it automatically sees, oh, we have a new object. It sends a message off to your RabbitMQ pod, which then you have some process listening to that as well and saying, oh, great, we have a new message. This is a level 0 binary thing that we have to process into level 1. It sends an API call to your We also have like an HTC batch job manager in cloud native areas. So it's the cloud native version of Slurm, PBS, HD Condor, whatever. It sends a job off to that, and that does its thing. That sends its output to a bucket, and then the cycle continues. Like, okay, we did level 1 of processing, well, we have to get all the way to level 3 of this product. So then you send another message out, you inspect that object, be like, okay, now I have this file, I have these other dependencies, is what your custom code can say, and then it fires off another job. And this is all done in an HA way in the cloud. And it all can be managed via the GitOps method that I was talking about earlier, which makes it a lot easier. So if you are at NCAR or some sort of associated university with us, basically if you have any access to our HPC resources or could get access to it through your university, as I mentioned, I'm on the internal cloud team here. We have our platform called Cirrus, which is cloud infrastructure for remote researchers, universities, and scientists. I think that's right. And it's just our internal way of providing resources cloud natively to people. It's a curated Kubernetes platform where we provide a lot of niceties on top of it to make it easier for people to use. And the big thing here is that we understand that this is a big shift in way of doing things. So we're also here to consult with, to help build, migrate, just think of ideas of how your applications can move into being a cloud native way and off of just a single server that's going to die at some point, and then you're going to have a really bad week. There's a link to our website down there where you can find out more information and how to contact us if you want to start talking about anything. And the main takeaways is that cloud native isn't all or nothing. It's very piecemeal. There's a learning curve. It's a lot, but I think the people here at NCAR who have started going down that have started to realize, wow, this is actually really useful and cool and worth the effort to learn. And we're here to help them learn that as well. Applications can be migrated piece by piece. You don't have to go re-architect your whole application in one go to be cloud native. We can take a piece of it, stick it in there, make sure it works, and then take another piece and stick it in there, make sure it works, and keep doing that. But it is also possible through containers, since you can basically recreate your whole existing environment to just do a complete lift and shift with almost no downtime. Of well, it works this way on the server, let's move it into an HA way in the cloud. And then after that, you can start kind of taking advantage of more cloud native methodologies. So it's just like a traditional methodology just shoved into the cloud native way. And in my opinion, I think it's blurring the line with traditional HTC computing, object clusters like Casper, which is HTC in my mind, become a little less important if you start doing things this way, cloud natively, because everything Casper does, you could probably do this way and slightly better. It's not going to replace Derecho or HPC or the really big supercomputers anytime soon, but it's interesting. And I think that was my last slide. Cool. Questions?
We need to keep moving along, but I actually did have one quick question. And I was really intrigued by the idea of functions as a service. Yeah. I was wondering if you had any advice for where to get started with learning how to do that.
I mean, if you want to pay for it, you can go just play with AWS Lambda or whatever. Otherwise, talk to me. We haven't actually deployed that at NCAR yet because we haven't really had anybody need it, and we're trying to until people need things, not deploy it. So if you want to do that, I've already have it picked out and half in my head how I want to make it happen. So I'd be happy to work with you.
Sounds great. Thanks again.
Yeah.
So our next presentation will be by Ben Kirk, enabling CI/CD for HPC applications with NCAR-ish development containers.
Thanks, and thanks to the agenda organizers for putting together a good session. This is a lot of good background material and good good talks to follow as well. So my name is Ben Kirk. I lead the HPC Consulting Services Group. And I'm going to talk about kind of a fun project that's become useful over the past year and hopefully forms the basis for using some of these technologies that have already been described a little bit more easier for our user community. So this started out sort of selfishly and ended up altruistically. As we prepared for the next round of procurements in our supercomputing environment, we looked at what we'd done previously. And so when we bought Derecho, there's a suite of benchmark applications. They were distributed as tarballs with checksums and make files and simple stuff like that. But kind of wanted to do a different job, or a different approach this time. So we envisioned that we might take that and distribute it instead in a modern CI workflow, but also with a containerized reference environment. So that led to the desire to have a portable HPC-like environment. That led to a desire to create some HPC-centric development containers. And that led to a different CI workflow to develop them themselves, enabled by Cirrus. And then now we have way more use cases than we originally envisioned. So that's what we're going to talk about today. So the stack looks quite a bit like what you would see on our base. On Derecho. I'm sorry, I got some bad news just a moment ago. So this looks a lot like the model environment you see on Derecho. At the bottom, you pick your architecture. It's either x86 or ARM, which is value-added. You then layer on a base operating system. We support all the Linux, SUSE, Ubuntu, and various flavors. Then you've layered on a toolkit environment. We support Conda, which is not pathogen build, and we'll let you install the ADL. If you want, CUDA, Rockham, things of that nature. And then it gets fun, right? So any of a compiler family, whether it's GCC, OpenMPI, or sorry, Intel's One API, AOCC, EB, HPC, etc. And then any of a supported MPI environment. Sorry, Sam. It's good. No, we're good. We're good. And then sitting on top of that is a set of IO libraries. So this is an intentional choice. It looks a lot like the default environment when you log into Derecho. So if you do a module avail by default, you'll see a lot of these packages, or at least a flavor of them. But there's no modules inside this container. Each container instance is a coherent environment. So when you take these together, there's about 50 valid combinations for a given operating system. And that's quite a lot. It doesn't include a module environment. It's actually not SPAC-based. And that was an intentional choice. I wanted to be able to build the entire software stack from source, sort of as a risk mitigation approach, but I think there's other reasons that become apparent as well. These are very lightweight. When they result, they're small and they can be downloaded easily. So it's easy to use in the CI as opposed to some of the bloat that can't be gotten rid of easily with SPAC. So anyway, that's the stack. You kind of pick a single version through that tree, and that's your instance. So how is this done? This was done with the newest, fairly recent feature in Docker is what they call multi-stage builds. And so if you've worked with Docker before, they usually begin with a from statement and then they end. A multi-stage build takes that idea and expands it a little bit further. Basically, you can have multiple from statements within the image itself. So rather than, from Ubuntu latest, do all my stuff, you have these multiple from points, and those can be different entry points. So they can also be different ending points. And so that approach combined with just some build arguments, which are effectively like environment variables inside the Docker file, lets you layer together dependencies. So my pointer's not working, but it begins with, there's like 5 or 6 different operating system entry points. You actually choose one of those, and then you can layer on top of it toolkits and MPAs, etc. And so the whole thing's a monstrosity. It's 1,300 lines, and all those dots are actually where the business is, right? That's the details of building in VHPC and tightening it up actually to make it fit in a nice small container. But that's the idea. So I used to do this differently. It used to be a pile of Docker files inherited from each other. That's kind of the old way. Is this new way better? I don't know, I'm not so sure, but it seems to be the way that it's done, and who am I to stand in the way of progress? This all started at Supercomputing 24, and it was a fun little side project. I honestly think I broke my old Intel MacBook doing this. That's a lot of combinations, right? My replacement MacBook is good at building ARM, but leaves a hole for the x86 variant. And then, so a little more than a year ago, Cirrus came online and was able to be used for this work as well. Kevin just gave us a good talk about some of the capabilities, but one of the things he used is a GitHub Actions scale set. That really handles the x86 problem. These are beefy nodes, they have plenty of disk space, and they have GPU access as well. I'm also using freely available GitHub action runners in the cloud. These are available free for open repositories. More on that in just a second. That gives me access to x86, 64, and ARM. They're fairly weak nodes. They're 4 cores on a VM with 16 gigs of RAM. 2 talks ago, we heard about GitHub Action, or custom actions. A fun aside with these free runners is they're kind of tight on disk as well. They have less than 20 gigs. And that's a little tight for actually downloading in VHPC plus CUDA, building all this stuff and getting an image. But I do have a custom action. So it's a VM, but you have root. You can uninstall a lot of that cruft and get back to 60 gigs of usable disk, which is enough to do that whole stack, with the exception of playing. Sorry, can't build playing within 16 gigs of RAM. Doesn't seem to be doable, or at least not a version of it you want to run. So when that's all done, they're published to Docker Hub. I tag them by CPU architecture, just so there's no confusion. But that's all implemented in some GitHub Action that sit on top of 2 different repos. One of those is public, so I can take advantage of these free GitHub Action runners. The other is private because it touches Derecho and Casper with some self-hosted runners. In retrospect, neither of those names make a lot of sense where the project is now, so happy to fork this out to something else. More on that later. But those resources are available and accessible immediately. If you want access to the private links, let me know. I'm not charged for this, but it is, GitHub does report usage. And so I went back and looked at what my GitHub Action Runner consumption was in 2025. And it looks like it's $2,500 worth of value, really kicking up there in July through September as that 1,300 line Docker file was matured. But then asymptotically, the thing hasn't changed a ton other than incorporating new versions month to month. And so you can kind of see what it takes to, from a GitHub Action Runner perspective anyway, to implement this. It's really easy to try locally if you have Docker installed. I'll talk slow if you can talk fast. It's not a demo. But anyway, Docker run IT makes it interactive because the first thing it does is going to basically launch you a bash shell environment. The naming nomenclature is operating system, compiler, MPI, and then optionally CUDA. But unless you need CUDA, don't download it because it adds about 5 gigs. Once you're inside, I tend to install everything into the /container path, which becomes a little more obvious later. But it's just a shell that's configured with the stuff you would expect. It looks a lot like a common module environment. I stop at the dependencies, but I have developed a set of build scripts that I use primarily in actually checking the container itself, right? Like if this container can't build Dart, or ESMF or something, it's not going to be useful with the community. So there's scripts within the container that kind of demonstrate how you would build some of these other applications or dependencies within the environment. And those are actually used when developing and CIing the container itself. So the container is not going to get released and tagged unless some of these scripts run, or all of them run. And if you want one added, PR, really easy. Probably though, what you want to do is use this in your own CI workflow, and I think we'll hear a little bit more about this in the coming talks. But a natural way to do that is with this matrix strategy. And so you can see, if you have really good eyes, about a third of the way down, there's this run matrix defined by the 4 entities: compiler, MPI, GPU, and architecture. So the outer product of that 4-dimensional matrix is what you're going to run. Combinations of those entities. And then you can exclude some stuff that doesn't make sense, like there's no Intel compiler on ARM, so we're not going to run that one. And then down at the bottom of the red box, container image, bam. It's going to pull the container image tag associated with the instance from the matrix. And then it runs the rest of your GitHub Action workflow. So plugging that into your application-specific stuff, so this shows you running the scripts from this build environment for Wharf and Dart and MPAS, etc. So it's really pretty straightforward. That'll work on obviously the freely available GitHub Action runners in the Azure cloud, or Cirrus if you have access to a runner set. This is what it might look like graphically when you go deploy that YAML file. You can see the green ones have already passed, the yellow ones are in work, and it takes maybe 10 or 15 minutes per instance in this case, depending upon how fast your compiler builds code base, for example. Obviously, not all the same. Let's see. Okay. Now, one of the things that's special, or design criteria for these, is we wanted them to work on Casper and Derecho as well. I skipped the point, but that's why there's 2 versions of InPitch within this suite. And so I've also created like utility shell script wrappers. If you launch any of these shell scripts, you'll basically get an interactive environment within the container, but also work on something like Blade, which is nice value added. So for example, I'm launching the NVHPC container with OpenMPI and CUDA. It tells me how to query the environment, and then sure enough, I've got NVHPC 25/7, et cetera, et cetera. So complicated, don't want to go into too much detail here, but yeah, the design condition is we want these to work with the host MPI integration on Casper or Derecho or wherever. And it does. The way that gets done is a little wonky. Basically, you require that you build an MPI inside the container, which is ABI compatible, binary interface compatible with whatever is on the host. And so that's taken care of by us. The way we build InPitch 3, for example, is intentionally chosen to work with Derecho. So that's done in the container, and then when you run it, whether it's probably an Apptainer, but with any of the HPC runtimes, you do some tricks to stick the HPC provided MPI into your container, so you're actually running against the host MPI, not a king container. It's kind of wonky, it's kind of gross, but it seems to be, again, the standard way of doing running containerized MPI applications under MPI performantly. So what's next? Getting beyond ish, right? These are NCAR-ish. They've kind of been a hobbyist thing for a little bit. I think they've shown some value for the community. Jury's still out, maybe we'll see by the end of the day. So we are incorporating feedback, happy to hear from early users. This has got, you saw the asymptotic cost there. This runs once a month by a cron job on the GitHub Action side. I will, there's about 5 websites I go look at once a month. Is there a new GCC? Is there a new Intel I need to work with? That could be, scraped with a day of, Claude and just some quiet time. So that should be automated, getting the new versions in. And again, I alluded to neither of the repositories where this is hosted now really makes sense long term. I'm happy to kind of work this out into a more community supported project. So yeah, that's it. I think we're 1 minute within time.
Thanks, Ben. Do we have any questions in the room? I'm about to check the Slido.
Thanks so much for your talk, Ben. We're really excited to start using the Cirrus capability, so it's cool to see this and to help figure out how we can start taking advantage. I had a technical question. So on the list of the software stack that you had way back early, you mentioned you're going to have Clang but not Flang. So I was wondering about that.
No, it's Clang. Clang as it, I don't know what to call the base compiler. Right?
Oh, okay.
So the Clang compiler suite built with latest Flang support.
Oh, so it does include Flang.
It's a Clang version 20 with new Flang in it.
Oh, okay.
Yep.
Perfect.
Yep.
Okay.
Just like GCC has GFN.
Yeah. Okay. Awesome. So the other question I had, the bottom layer, the architecture.
Yep.
So if you're running on a machine, is it emulating a different architecture? What does that mean?
So it can, and you don't want to. Typically, certainly not for HPC.
Exactly.
If you have an M2 or 4 or whatever, that Rosetta chip will emulate x86. Docker can pull an x86 image, and you can run the Intel compiler on your ARM Mac.
Okay.
And from a performance perspective, not great, but if you like to write software on an airplane like I do, I mean.
Okay. Okay, so it just allows you to test different architectures. Okay.
ARM was
perfect.
Definitely, we don't have a lot of ARM hardware, certainly not in production around here, and so I thought it would be valuable for our community to like CSM has assembly in some of the build paths, and it's like you want to catch that if it's not running on ARM, for example.
Okay, perfect. Yeah, thank you.
I have a question that, so if we use container, you keep upgrade those containers. So when we use it, we will not notice that upgrade, or we have to deliberately upgrade?
Yeah, so probably getting from ish, right? There you go. That latest tag is latest, right? Whatever we got built last. There's also a year.month nomenclature, right? So you could pick 26.1, and that would be January version of this. There's not a great public-facing information about what the exact version's in that, but that's it's in the Docker image itself. It's just like not exposed to the website, right?
Okay, thank you.
So, but the best approach to, if you always want to run latest, just stick a script, a shell script in here that tests the application. And then, these are tests from release, right? Like I don't want to be, they're not tip of main of any of these branches, but, making sure that it works with the latest release versions of, target applications.
I feel like you could ask a quick question.
Hi, Ben. Apologies if you kind of explained this and I missed it, but I imagine like CSM, for example, has certain dependencies that like Wharf doesn't need and vice versa. So is there any thought, because it seems like we obviously now have a container that can build both, but is there any plans or future for like, okay, here is a CSM container that's smaller than the bigger one and a Wharf container that's smaller than the full one? Basically ones where it's built only for those applications.
So the trick, the thing is those libraries are real life.
Oh, okay.
Right? They're, they add almost nothing to the size of the container. You can easily remove one if you truly don't want it in there. But I found that, a shared library installation of that whole IO library suite maybe adds a couple tens of megabytes.
Oh, okay.
What you'll hear from maybe in a talk or two is if this isn't enough and you want to add more complex special purpose dependencies, you can imagine another layer, right? Where maybe you derive, you take these and you add, maybe you don't want to recompile the SMF or you want to.
Right, cool, thanks.
Okay, great. Thanks so much again, Ben.
Thank you.
Okay, so our next speaker is Cena Brown with their presentation, adding automated testing to MPAS-A, and you can too.
Right, yep, I'm Cena Brown. I'm down from Laramie, Wyoming for this conference, and it's been so wonderful seeing everyone, so thank you.
Can you move the mic closer towards your mouth? Thank you.
Yes, thank you. All right, well, I just got set up perfectly by the talks today with so much focus on CI and containers, so I'm really happy to share kind of the practical applications of some of the past talks and all of the setup work. Sorry? There we go. All right. So the MPAS project needed testing. Hasn't had testing incredibly enough. And I really think of this as a co-development project. This is a lot of scientists and a lot of engineers working together to contribute to this beautiful code. And the scientists, they're looking for ways to test out new science without breaking everything. And the engineers are looking for ways to optimize the code without breaking that science. I'm on the engineering side, and I will tell you that we also break the code ourselves. It's not just the scientists. I remember starting off as a student researcher for NCAR quite some time ago, and in a windowless room with other undergraduate and graduate students, first working on doing some open ACC porting for MPAS. And as a group, we agreed that, yes, we were under the impression we're switching to open ACC, so it is fine to remove all that open MP decoration that we see. We'll just delete that as we go. I felt really guilty about that for a while. So, and this heart in the middle, holding this all together for this project is Michael Duda. And the scientists and engineers are just squeezing. So, it's this project for me started as I really wanted to give Michael Duda a tool to help address the PRs that he's receiving, which, you know, and with the advent of LLMs are only going to be increasing in complexity, we really needed to figure out a way to help. So this is what we've built so far. Full matrix of testing for MPAS, which, you know, what is a full matrix? We kind of define what that means, I guess. But across compilers, MPI libraries, the IO stacks, different IO stacks for MPAS, and then also hardwares, CPU and GPU. The testing now has statistical validation. And by that we mean we're not just looking at bit for bit reproducibility, which is great for some things, but the ensemble consistency test, which was developed here at NCAR, is also implemented in the testing workflows. And so that doesn't require the bit for bit reproducibility. We're using containerized builds, which, thank you, Ben, for going into detail on that, because we are using Ben's containers and they have been wonderful for getting this project off the ground. And we can use this, our CI workflows for testing in our repository, which is NCAR/, MPAS model CI, and we'll have a link up there, as well as the main project repository, MPAS dev, and then all of the many forks which exist for MPAS. All right, this is kind of what we're talking about when we describe the coverage matrix. And this matrix was developed in conversation with Michael of what would help you, what needs to be tested, what do you think we should be focusing on. And so for CPU, we're doing GNU, NVIDIA, Intel. We also are doing an OpenACC build on the CPU side. So obviously we're not running it if we don't have a GPU, but it is still a good quick test. I kind of crossed out MPitch 3 because I realized I had stopped testing it, but it is available to us as an option. PIO and SMEAL IO libraries. And then one and just like a little 4-rank test. And then on the GPU side, on Cirrus, thank you to the Cirrus team, we're doing our OpenACC build and runs and testing the IO libraries and MPI as well. So far I've described 2 miracles that have happened to make this project be able to really get started. And that is 1, Ben's containers. And then 2, it was like, how are we going to do CI testing for MPAS when GPU testing is so important and GPUs aren't available on GitHub Actions? Well, then Cirrus comes in and makes GPU testing possible for us through the CI. All right, the ensemble consistency test. So the way this test works is that you take your initial condition file and then you perturb it at uniform random distribution of perturbations at the bit level, double precision bit level, just in the temperature field. So you do this and you create 200 different initial condition files from those perturbations. And then you run MPAS with each of those different initial conditions. Do statistical analysis using the PySect library, which calculates the ensemble statistics. So it'll describe the variable output from your perturbed runs as kind of a curve with some understood variance and distribution. And then for every new configuration of MPAS that you want to run, you run 3 more perturbed versions, and you compare it, and you see where it falls along that curve, and you see if it's consistent with, like, would it reasonably be in that same distribution? And if it is, you can say that it is consistent, even if it's not bit for bit. And this is so useful for testing across different compilers, different hardware, especially CPU to GPU, where we don't expect bit for bit reproducibility. So that's their paper. And the other cool thing is, and to be aware of, is that you would expect the ensemble consistency test, you need to rerun it when the science changes. So this is really great for comparing optimizations or, new code that you wouldn't expect to change the variable output. But when there is a new science release for MPAS, which we're about to probably any day here have a new version released, you have to rerun the ensemble. And it's been kind of a pain doing that. But it is now also automated. So it makes it quite a bit easier, and the ensemble generation is tagged to the MPAS dev version as well. So this is an example of, you can see the building of MPAS. I forgot to mention there's a 24-hour spin up in there because we're running a moist version, and we want there to be time for like clouds and things to develop. So it's an initial condition file that's been spun up for 24 hours. Then you perturb it, generate the summary statistics, and then they're published on the repository along with the data that was used to generate everything. So hopefully it makes it a little more documented and easy for people to run on their own. All right, this is an example of what the ECT puts out. So when you run on a new pull request, there will be some text describing the PCA that is done. And yay, this one passed. There were, a few little failures, but it's to be expected. It falls within the curve. All right, so then on the README page as a summary, we have all these badges that now describe whether all of these combinations passed the ECT. If you look at the README, there's actually quite a few more badges also describing code coverage and bit-for-bit testing as well. But yeah, and if you click on any of the badges, it will take you directly to where that workflow was run. All right. Yes, so we've, for this project, also gotten into these composite actions. It's very helpful for not repeating yourself constantly and not needing to update many different places in your code every time you want to, for example, change the test. So, we can swap out doing an ECT test versus just a really basic log comparison pretty easily. But we have started to develop these composite actions, which means that they're just a few steps that aren't expected to be run independently. They're expected to be run as part of a workflow. But that has been made things much easier and organized. And the other really neat thing is that these actions, like so many of the speakers today have said, can be shared between projects, and especially within the organization. So the workflows that run kind of automatically when there is a push or a PR are the testing the 3 compilers on CPU, along with mpitch, because that's the default we wanted. And then we have additional workflows that are triggered by dispatch. And we're also especially careful to only allow admin dispatching onto the GPU callers onto Cirrus because of security concerns. We've also set up some special workflows that are for kind of debugging purposes. The bit-for-bit unit tests, which is, I'll come back to the unit test. But then the ensemble generation, a standalone ECT, and then the cross-repository testing. All right, so code coverage. This was a workflow that helps see what code is actually being run during your testing. And it's currently pretty low with this current setup of the ECT. We could probably boost it up with some unit testing. MPAS is very difficult to get started there, but again, we'll come back. And this will at least let us know if we can design more tests to increase that coverage. Because obviously, if we're running all these tests on code that isn't even being executed, then it's not very valuable. All right, so some features in progress. Linting for Fortran. It's difficult. We've set up a few workflows with the traditional linters, but where we're at right now is setting up Copilot instructions, because we have Copilot automatically reviewing the PRs, and you can set specific Fortran linting and syntax instructions for that. So I think that's a great use case. Unit testing in progress, and I wanted to say a huge thanks to Quan Chi with the CAM-CMA MPAS project, because he got this set up and we were able to just drop it right in to the standalone MPAS. So the PF unit framework is up and running, and there's that one little spline test that's also running. But the dynamical core of MPAS is like pretty difficult to break up. But I think there were some really good points made about, even if you don't start with the test-driven development and you don't start with all the unit testing in place, any testing at all is going to help. And progress in testing in one area can lead to making it possible to refactor the code easily to enable unit testing. So for example, like if you told me that we had to refactor the dynamical core into something, more testable, it really helps that we have the ECT set up so that during that refactoring process, we can be confident we're not breaking everything. As part of this, I also set up a contributors guide. This was also done in conversation with Michael Duda, getting all of his feedback over the years of doing code reviews, getting it written down in one place. Hopefully that will make his life a little easier when he's, reviewing PRs, and really helps everyone in the community to know what he wants and how they can improve it and reduce the turnaround time on those PRs. And then performance testing, especially for GPUs or, GPU porting, the goal is to go faster. So it's interesting to have been doing all this testing, and we're not really talking about timing. And there are some challenges there because, if you're running it on GitHub Actions, you're not always sure exactly what resources you're going to be on, and they're probably not going to be dedicated just to you. And so, what is your performance data really telling you in that case? But I think I know Quan Chi, Anthony Eilis, and then Ben was just describing ways to run some of these containers on derecho. And they have also been working on that. And so I'd like to explore if we could get some real performance data out of this testing. All right, so some quick takeaways and things that I've learned. When I was first starting out doing, building some of these tests, I started out with huge matrices. And it was so cool. But it is not a very clear signal to interpret. So I have switched to doing just like small subsets. And part of that is because each job, that is all one job. testing all of that. And that job can only report back pass or fail. And so it's a very binary outcome. You can obviously, if it fails, you can dig in to all of this, but it's not providing you that really quick feedback. And it's just a Rube Goldberg machine of trying to keep it all green. Then the other thing that I've moved to that I thought was really helpful is besides just the modular, moving in a modular direction of like the reusable actions and the workflows that are using those component actions. I've also set up a CI config file. And the idea here is that it can hold on to the settings that we use for container tags, container versions. We can pin things there. We can also have all in one place our settings for the ECT test and the bit for bit test. It kind of provides a way, I hope, to avoid people needing to dig into those YAML files as much. And then one other thing is that container maintenance is a huge learning curve and really, really high overhead if it's done by each project on their own. So I really have been encouraging anyone to try to use the Sizzle dev containers or HPC dev containers. Even if you realize that you would like to go back and make your own custom container, I would say think about it again. And then, because these are set up for, to really help things along when you want to do scaling jobs on NCAR, on Dorito. But yeah, just, get the hang of it and see what you really need there. All right, I have so many things. But the containers and system support, it's been Kirk, Kevin and Nick on the Cirrus team. The ensemble consistency test, our group, ACS, has Teo Price Brancuccia and Allison Baker, two of the authors on that paper of applying it to MPAS. So, whew, that was great. And then MPAS-A development team, Michael Duda and Abhishek Gopal have been really helping inform the way this testing went and giving great feedback. And then CI development, so many of you in this room I've talked to and have helped. Haing, Jen, Lily's been helping with the contributors guide, Lalo and Michael and Sherry and Sam and Dan, Quan Chi, Jesse, and Anthony Eilis. So yeah. Oh, there's the repository where it's living. And I think if we all, I don't know, like clap our fingers or snap our fingers, maybe Michael Duda will let me move this into the main MPAS dev repository. That is the goal. And we have a hackathon at the end of this month. And so our agreement that I've told him is that we're going to really test this at the hackathon, and then we're going to talk about moving it into the main. All right, and then there's the Read the Docs Contributors Guide. Yeah. Thanks.
So I'm not seeing anything in the Slido, and in the interest of time, we should probably just move along. So thanks again, Cena.
Thank you.
Okay, so for the final talk of this session and the conference, we're going to have Lalo Torres with their presentation, Continuous Integration Using Project-Specific NCAR-HPC Containers on the Cirrus Cloud.
All right, thanks. Yeah, I'm just going to, I think, take it away because of time here. So we're just going to go a little bit faster, but I feel really set up well because I'm going last. I also know I'm fighting an attention deficit because I'm going last, so I'm going to keep that in mind. But the thing that I want to say is that I want to set the problem first. So I basically am a software engineer. We're working on a project. Our project lives out in GitHub somewhere, and our project has dependencies. So there are like other libraries, compilers, tools, runtime stuff that we use that is not really code that we're responsible for maintaining the repository or even doing anything with. We're just consuming it right inside of our project. So this is very common, amongst NCAR, many developer workflows. We have these external dependencies that we have upstream from our project. We're not really contributing code back into the compilers or CMake or MPI, but we're using that stuff, as well as some maybe more niche stuff like AMRX is one runtime environments, performance portability runtime environment that we're using in our code. So I just wanted to start off with that separation of we have things that we use, and then we have code that we're actually writing, and that lives in our GitHub repository. So how do we use that code in our GitHub repository? I think that I'm pretty well set up here as well, especially after Michael's talk this morning. So we basically, if you think of like we have, some source file if we're sitting in main, and inside of that main, we're just including stuff. And this stuff is what sits in those external dependencies that are upstream. And after we include it, we can use it. This is a C++ example, but in Fortran, we just do module use, same idea. And our build system only knows about these externals through, in this instance, we're using CMake. We can just say like find package, the package name, and it's required. So if at compile time for our project, it can't find that package, it's just going to throw an error and the build won't continue, right? And again, like Michael said in his talk this morning, whenever we want to link against it, we can just say, I have something called main and I want to link it against something called AMRX, and that just works, right? Because we're in our build system. So we have a bunch of different people. We're a distributed team, even on small groups. I feel like everybody works in different environments. So like I'm over here working on my laptop that's running some flavor of Linux. We have people in our group that are running on Mac, so very popular here at NCAR doing local development. And then we also have people on our team that like to do their development just right on Derecho. They get on a login node, and they're, we all have local instances of our shared GitHub repository. We're all adding to codes, making commits, pushing back to main, that kind of stuff. And these are all very different environments, right? So we're getting different compiler versions, different versions of the libraries that we're dependent on all the way down the dependency tree. But whenever we commit into our GitHub repository, we have GitHub actions that run. And the idea is that these GitHub actions basically just launch a container. And inside of that container, we already have all the dependencies that we want for our project. So there's already some specific version of a compiler, in this case, let's say GCC, and some specific implementation of MPI, and so on for all our dependencies. So we really want these containers that run our CI to be the standard environment that our project is sort of measuring itself against. So if it runs in the CI containers and somebody's local environment breaks, then it's probably your local environment's fault, as long as it runs in all of our CI containers, right? And this is true for a matrix of them. So we have different compilers, different MPIs, and these all run automated via GitHub Actions. So I feel like I don't need to go too much into detail about how this works, just because of all the talks that came before me today. I feel like this is pretty well set up and understood that we have GitHub Actions, they fire off containers. The containers are turnkey environments. They already have everything we need for our project, and it really simplifies our CI workflows. Basically, our CI workflow says, launch one of these project-specific containers, and then just run make and run test, and that's it. And make doesn't build anything but the code that we wrote in our repository, and test doesn't test anything but the code that we wrote in our own repository. So all the dependency stuff is handled ahead of time. This is basically just, I want to put my environment in a box. So I have these dependencies like compilers and IO libraries and unit testing frameworks and all that. I just want to put it in a box somewhere and I don't want to worry about it. I want to be over here on the right side of the screen, working on my own repository on whatever machine I'm on. So the tool that I ended up using to put our environment in a box, and there's a couple different ways to do this, but I went the SPAC route. So SPAC was very convenient because I could take that exact same picture from the previous slide and essentially just turn it into a YAML file. So this is our actual YAML file for our project. I really most of this is boilerplate created by SPAC. If you just say SPAC environment create, I added 5 lines, and it's just the 5 package names that I want to include. So I said, I would like CMake, AMRX, MPI, my Google testing framework for unit test, and HDF5. And that's the only input that I gave it. And that really sort of is the basis of how we spin off these environments. If I just say SPAC install on this environment, so I'm going to get this big, DAG, it's spaghetti monster, right, of all these different dependencies that SPAC goes off and builds. And what I want to discourage people from is being afraid of this. Basically, I know that you guys can't see it because it's too small on your screen, but these are the 5 packages that I installed. They're way up here on the top right. This is AIMRX, HDF5, Google Test, CMake, and MPI. And then all this other stuff down here are all dependencies of the things that I wanted to install. And I really don't care about them. It has SPAC will get very specific. It will tell you exactly what version number of, like what version of zlib is HDF5 using, and is MPI using that same version of zlib? In this case, yes, but most of us, if we're just writing our application that uses MPI, we don't really care about the dependencies of the dependencies of the dependencies of MPI, right? So I know that this looks complicated, but basically I just take my 5 packages, which sit all the way up here on the top. I say install, and it goes and figures out everything underneath it. And I really don't worry too much about that, right? About all the dependencies. You could go in and say, like, I really would like to use some other version of zlib. There are ways to tell SPAC that, but I want to keep it as simple as possible for our build. I just want to say, I just care about these 5 packages that I'm directly using my code. I don't really care about all the sub dependencies. I just want to keep our build simple. So that looks complicated, right? But how do we use these views inside of SPAC? So basically, SPAC, whenever you launch up one of these environments, it gives you this environment variable called SPAC env. So this is automatically populated. And inside of this directory, there's something called view. And this just looks like root on your own machine. So this has the things that you're probably familiar with. This has a bin directory. This has a lib. This has include, right? So instead of just linking to root lib or root include, you just link to this. And it conveniently also has one for CMake. So if we're using a CMake build, we can just say this is in our CMake prefix path. And now all of our CMake stuff should work for whatever packages were installed with CMake. But if you're not using CMake, this still is convenient, because essentially just looking inside of what is inside of that view include, it's all the header files for everything we installed. So in my example, I show linking against AIMRX, or including AIMRX. So it all sits in this include file. So these are actually symbolic links. So if you're thinking, oh, I don't want all these different copies of these files running on my machine, it's kind of faking it for you here. They don't actually live in this directory. It just creates all these symbolic links to all the header files to everything it installed in your library. So it looks complicated in the last slide, but it's very easy to use. You basically, instead of linking against, root include or your specific dependency include, you just link against, or you just include your SPAC environment include, and that has all the header files in it. And same for lib and everything else. All right, so for that first example, though, I basically just used the YAML file on the left, and it was super generic. I didn't say anything specific about what compiler to use. I mean, MPI is like not really a package itself. There are different implementations of MPI. I didn't say that. I just said, SPAC, take the wheel, do whatever you want. I don't really care. I just want these 5 things. But when we do this in reality, we basically have a bash script that creates these environments for us. And inside of that bash script, we just on the fly add a couple of things to it. So like I always end up saying, I would like you to use some compiler. So like we have an environment variable called compiler spec, and I literally just set that equal to GCC or LLVM or whatever compiler I want. And the same for MPI. Like I would just I have an environment variable called MPI spec, and I would just set that to OpenMPI or MPitch, and then it will use that instead of making its own decisions. So we kind of have this separation on, we keep all of the stuff that's dependent or independent of whatever environment we're running in one YAML file. And then whenever we're building an environment in a specific context, we have a couple environment variables we can throw at it, our little SPAC environment create script that tells it we have additional preferences. Like I would like you to use a specific compiler or a specific MPI or something like that. So we kind of keep this simple base plus a few preferences I might have at any given environment. And now we can generate a bunch of different these giant DAGs or spaghetti monsters. Each one's its own environment, right? So the first one I showed was GCC OpenMPI. But if I run through my matrix of compilers and MPIs I want to use for CI, each one of these is going to be different. And you might say, why is that different? Why does it use a different dependency and all that? I think as an application developer, I don't really care. All I care about is the 5 packages that I asked for there. So all these sub dependencies and sub dependencies, I'm not too worried about. And each one of our indices in this iteration space for this build, for the CI matrix, produces a different environment. But they all have those same top level 5 packages in them, right? So now with that one script sort of running in a loop, all I did was change the environment variable from GCC to to LLVM or something else, and the same for MPI, I generate all these different environments, right? And this is very convenient for me being like a developer for our project, because if at any point I want to test with, I don't know, LLVM and MPitch, I can just launch, our project environment, LLVM MPitch, and it will pull out the right one of these, and I can just build our code and see if it runs correctly, right? But this is a talk in the title. We're talking about running these inside of containers for CI, and this is all still running on my local machine, right? I just spun off all these environments here. So the next step was, okay, now that we got all this debugged and working, we want to run this in our CI actions on GitHub, and how do we put these in containers? So we basically just put it inside of a Docker file. So the exact 2 steps that I said, we just we use some generic base container, Ubuntu latest, the most, probably widely used or one of the most widely used containers. Inside of that container, we just do the previous 2 steps. I'm going to install SPAC. I'm going to install my SPAC environments just like I showed you guys previously, and then out comes a new container. And that's what we're going to call our project-specific containers, right? So I just basically throw my previous bash script in a loop with a Docker file in it. And now we have a container factory. So for each one of these cases in our CI matrix, we can push out these containers that have all of our dependencies in them. So this is very convenient. And I could say, mission accomplished, we're done, right? We have containers that are project specific. It has all the stuff that we care about in it. All we have to do is spin up any one of these containers in our CI actions and say, essentially make and test. We don't have to install anything else. It's just going to test our code. So we wanted to go a little further because there are other environments that we run in. So I'm just going to go back to bare metal for a second and get out of container world. And so at NCAR, we have everyone on our projects basically running on Derecho, which already has a lot of this stuff installed. So you don't want to reinstall MPI on Derecho. You don't want to reinstall compilers if you don't have to. And so CMake is there, HDF5 is there, and we're like, we just want to use the stuff that's already installed on the machine. But for instance, there is no AMRX module or there is no GTest module. And I don't know how much available or how many people are using it or how it's configured for other groups at NCAR. So we don't really have a case to make it a module on Derecho that's shareable with other people. We're really just using these 2 in our project. So can we use them externally in our SPAC environment and still keep the rest of our essentially build and run scripts running? The answer is yes. So inside of that same script where previously I said I have some preferences about what compilers and what MPIs you use, this is literally taken out of our script, is just saying, if I'm on Derecho, SPAC external find these packages, and it will go run off and say, these already live in modules, you don't need to reinstall them. And I have the same 2 lines specifying our compilers and MPI. But the cool part is now our DAG, or this giant spaghetti monster, is super simple, because all of the nodes that I've put these yellow boxes around are actually modules on Derecho. So we're not installing those with SPAC. It's just finding them as externals through the module system. So the only 2 things that we're really installing for our project are AMRX and Google Test for our unit testing framework. So that's really nice. But again, this is still bare metal. And I feel like I was set up really nicely by a couple talks today, including Ben's. So we have these NCAR, like HPC dev, these NCAR, these Derecho-ish containers, right? And they have some of this stuff in them as well that's very similar to like that build that I just showed you via Derecho. So I just basically want to do the exact same thing and say, okay, like maybe I need a newer version of CMake than what's in one of those containers, or maybe CMake isn't in one of those containers, but these other things are, and I don't want to rebuild them because they're already configured to look like they do on Derecho. So if I want to do my CI in a container, I can use the NCAR base or the NCAR HPC dev containers to do this. And again, we have another block that just says, if my machine is a CI container, then I want to use these external things. We can tell it, you are not allowed to build any of this stuff. So like, even if you can't find it, that's just a fatal error. And I can give it path names as hints, like say, I know where HDF5 lives, so I'm going to tell you where that is, and you can't build it, right? So it's very easy to have this sort of way to turn on or off what SPAC builds, right? And we essentially just do this now inside of our Docker file. So instead of using previously, this was Ubuntu latest, now I just use one of the NCAR HPC development containers. And I have a couple environment variables I set, mostly just about paths for where things live. So I had something on the previous slide called like HDF5 root. So we'll set that. And that goes into our Docker file run, and out comes our new project specific container. But the main difference is we just don't install some of the packages. We just find those as externals because we know they're already in the container. So we've basically gone through this Punnett square of all the builds, I feel like. So we started off over here on the top left where I was doing things on bare metal and we installed everything with Spack. So every dependency all the way down the dependencies tree we installed. And that's probably the easiest place to start, easiest to debug. You're on your local machine. Anything goes wrong, you have interactive access, you can fix everything just fine. And then after I got that working, I said, okay, I'm going to throw this inside of a Docker file. Really, I just called the same script inside of a Docker file. And I'm just going to take the most generic base container I can think of, Ubuntu latest, and now we're going to produce all these different environments into containers. But we also had this other bare metal use case in Derecho, where I wanted to install some of our dependencies with Spack, but some of them I didn't want to. I didn't want to reinvent the modules that are already on Derecho and optimize for that machine. So that one was also relatively easy to debug because, again, I can log into Derecho, I have interactive access to debug anything. And then finally, over here in the bottom right, we had the container already has some stuff installed in it that I want to use. So don't install everything, but this is going to go into a container as well. So it comes from a container as well. So maybe a little more of a pain to debug if something goes wrong, but still not terrible. The main thing is that we didn't have to do any of this like environment debugging really through our CI actions on GitHub. So what you really don't want is if we had installed all these dependencies in our GitHub actions, every time something goes wrong, we need to relaunch those actions. It's really annoying. I know there's ways to run some of that stuff locally, but it's really slow. And one thing I wanted to emphasize was because of our test matrix, we basically had 6 in each of these 3 boxes, different environments. So 3 compilers, 2 MPIs, and 1 here. So we had like 19 or 20 different environments that we wanted to build with. And I stopped counting at 200, but there's like hundreds of different packages that get built through Spack because of this, with many more hundreds of dependencies between them. And you might say that sounds really complicated, but really we only had a 10-line YAML config file for Spack. That was the list of stuff we wanted to install. And we had about 10 lines of code of extra commands that we gave to say, I prefer you use this compiler over that compiler, or like, I really need you to use the version of HDF5 that lives in this directory or something like that. So a little bit of customization, but all these different environments, all this complexity, we're really able to control, I think, with just a couple lines of code, which again is very useful if we are going to be responsible for maintaining all these different environments. So just a quick summary. So we did generate these project-specific containers that are turnkey solutions. So they will build and run our project. All we have to do is run, make and test, essentially. We don't install anything in our CI workflows. It really simplifies them. It makes the CIs run faster. All it has to do is get the container and, we're ready to go, essentially. It also provides a common set of environments for our project. So if somebody says this doesn't work on my machine, then we can say, we know it works for all these different CI containers. So if you want to run the project, you can pull one of the CI containers and see what the difference is between your machine. But, we sort of has this stuff stamped out. And also, if one of our CI runs fail in one of these containers, then we don't have to go through the process of debugging it through the CI runs. You can always pull one of these containers locally, see how your code broke it, fix it, and then after it's done, push, and then it should run the exact same because you're in the same container. I'll skip future work. These are still kind of big. We want to reduce size and that kind of stuff. And this isn't using the GPU stuff, but I saw Jan's talk yesterday and he's doing that. So I think we can probably double dip there. I didn't touch too much on where we ran these, but the nice part was it didn't matter a lot. We could run these on GitHub Action Runners or on the Cirrus Cloud. Everything we're running is inside of a container. So any environment that can launch a container can pretty much do this workflow. Just because, again, our workflows are very simple. If it can launch a container, it can do it. Just a plug, we do have meetings here for CI/CD, kind of like a working group every Tuesday. So if anybody's interested in hearing more about this and you're at NCAR, then you can always join those. But I know I'm the last talk. I'm the last one before lunch. So any questions at all? I think that's all I got.
Yeah, so we are over time, but it's the end of the conference, so we have plenty of time for your questions.
Well, it is lunch, so.
Yeah.
Thanks so much. That's really cool that you can do that much testing with 10 lines of code. That's blowing my mind. But a question about AMREX. You talked about AMREX, and I think some other people talked about it. I was looking at it a little bit. It looks like it's runtime environment, but it also has like grids that you can, manage some stuff inside your code and things like that. Can you talk a little bit more about what AMREX is?
Yeah. So it's
go ahead.
Yeah, it's basically one of the performance portability libraries coming out of the DOE Exascale Computing Project. It's been around for a while. The nice part about it is that it's really centered around distributed memory structured arrays. So like if you're running on a structured grid, even if you're not using adaptive mesh refinement, it's probably can automate a lot of the performance portability aspects of targeting different hardware backends. So like we have some code that does some kernel math on structured grids, and we don't want to rewrite it for CUDA and for HIP and for x86 and whatever other hardware comes out in the future. So it's sort of a middle layer for that we're really using. The AMR in the name is for adaptive mesh refinement, but for instance, the project that I'm working on for this work, we're not even using the adaptive mesh refinement yet. We're just literally using it to get distributed memory multidimensional arrays that are performance portable. So. But if you're interested, yeah, we could definitely chat about it because we have examples of what it looks like in a mini app too that we developed that uses it. That's pretty understandable, I think.
Right. And in terms of the runtime environment, does that mean you run, instead of running MPI run or whatever, you run some AMREX thing that probably calls MPI underneath? Or
you still just MPI run. Yeah.
Oh, it's still MPI run.
Mm-hmm.
Okay.
Yeah.
So what is the run? Why does it say runtime environment? What part does that play there?
Well, for me, it's just, I should say that there's a difference between, and this is sort of a SPACism, but there's like in these spaghetti monsters, there's all the green stuff or the orange stuff on the right is like, those are packages you need to build the dependencies, but after you build them, you don't actually need them. And then the stuff in blue, I believe there's different, I think blue is run. They have like build, run, test, and debug, I think are like 4 different instances. So by run, I mean like I could get, after I build my container, I can jettison all of the orange stuff. I don't need it anymore. But the blue stuff's got to stay because, like AMRX uses MPI, so I can't get rid of MPI because then it won't be in my run. Whenever I run my executable, it won't be there. So.
Oh, okay.
Yeah.
Okay. I get what you mean there. Okay, cool. Thank you.
Well, awesome. Thanks, Lalo. I just want to say, since the conference, can we first thank all the speakers for the past 4 days? I appreciate it. Thanks. I also want to thank Multimedia, Fletcher and Kelvin. I think only Fletcher's back there, but thanks for keeping everything going. And finally, she's not here, but I wanted to thank specifically Samantha Scalise and the rest of the Sizzle admins for doing like 90% of the back of this behind the scenes work. Like, I just assumed food magically showed up. Apparently it doesn't. You have to tell people. So, yeah. So I just want to thank you, and you can thank her out there, but I'll thank her here officially. Awesome. And yep, so there's lunch, but otherwise this is the end of the conference. Thank you all for showing up. I appreciate it, and have a great rest of your day. Awesome. Thank you all. Thank you. Thanks.